On a calm night in early July 2025, a new point of light slipped into our awareness and kept going, faster than anything the sun could hold. It traveled on a hyperbolic path, retrograde to the motion of the planets, yet skimming close to the plane where most worlds circle. That geometry alone asked a question. What draws a traveler from interstellar dark to pass so neatly through our neighborhood, then leave forever? Over the coming months, a second question emerged from its chemistry. The object woke early, far from warmth, and its breath carried an unusual balance of carbon dioxide to water, a ratio that does not sit comfortably inside our familiar boxes. A third question arrived in whispers of light and radio, hints and rhythms that invite patience rather than proclamation. Together, these three clues form the spine of our inquiry. Orbital geometry tells us where it came from and why it is hard to catch. Chemical signatures hint at how it formed and how it sheds itself into space. Electromagnetic traces test whether nature alone explains the dance we are watching. The dates ahead matter. A Mars flyby in early October promises a closer look. Perihelion near the end of October may hide more than it reveals, simply because Earth will be poorly placed to see it. In this film, we will follow evidence, not hopes, and let uncertainty speak. If careful curiosity is your language, stay with us, subscribe, and join the watch. The discovery felt almost ordinary at first, the way most important things do. A small fast point moved against the background of fixed stars in early July 2025, and the pipeline that turns photons into alerts did what it was built to do. It linked a few short trails into a candidate, assigned it a provisional tag, and asked for another look. That is the quiet rhythm of modern sky surveys. But ordinary gave way to unusual as the follow-up astrometry accumulated. The best-fit orbit refused to close into an ellipse. The curve that matched the data was open, its eccentricity greater than 1, a textbook hyperbola. On paper, that simply means the object is not bound to the sun. In practice, it means we have a traveler that came from outside our gravitational well, and, unless acted on by something large, will not return. To understand why that conclusion matters, it helps to picture the geometry of our solar system as a shallow tilted plate. Most planets and countless smaller bodies orbit in a narrow band called the ecliptic plane. It is not a physical surface, only a convenient reference that emerges from the shared history of disks and dust that once circled a younger sun. When a new object arrives and slides almost along that plane, it earns extra attention because chance alone more often sends interstellar visitors from steeper angles. The discovery arc suggested just that peculiar alignment. The inclination looked large in the sense that its motion was retrograde, opposite the dominant direction of planetary orbits. Yet the object's path nearly grazed the plane itself. You can imagine a swimmer cutting across a river, heading upstream, but staying nearly in the river's central channel. The combination is statistically rare without being impossible, and rare is enough to provoke a deeper look. The numbers that first put the word interstellar on the table came from two simple ideas that every student of orbits meets early. The first is escape velocity, the speed needed to break free of a body's gravity. Near the distances where the object was measured, that threshold has a known value set by the sun's mass and the object's distance from it. The second is the relation between speed and shape for paths around a gravity source. Ellipses are for the bound, and hyperbolas are for the unbound, with parabolas at the knife edge between. When the measured sky motion is turned into a space velocity after correcting for Earth's own movement and the projection effects of perspective, the answer can land on either side of that knife edge. In this case, it landed comfortably beyond it. Even when uncertainties were included, the velocity at that distance implied a positive excess speed relative to the sun, which orbit calculators call V infinity, a small but non-zero number that marks the difference between a near miss and a capture. It is tempting to treat those results as final. I would caution patience. Early orbits are sketches drawn with few lines, and the sky is not a laboratory bench. Astrometric errors, especially for a small, diffuse target, can tug a fit into shapes it will later abandon. When an object is faint and moving quickly, short exposures stretch it into streaks, and measuring the center of a streak is less straightforward than measuring the center of a dot. If the seeing is uneven, if the tracking drifts, or if the reduction pipeline underestimates an uncertainty term by a sliver, the inferred speed can shift by just enough to change adjectives from merely fast to outright interstellar. The discipline absorbs this by revising and revising again, adding tracklets from more nights, cross-checking with independent telescopes, and letting the error bars collapse only as the data earn it. There is another wrinkle for active bodies. A comet sheds mass as sunlight warms volatile ices and vents form. Those subtle jets can push on the nucleus like tiny thrusters, introducing non-gravitational accelerations that classical two-body orbits do not capture. The direction and strength of those forces depend on shape, spin, and surface texture, most of which we do not know when discovery is fresh. Modelers can add empirical terms to fit the data, but the risk is clear. If you let the model become too flexible too early, you can fit noise and call it physics. If you refuse to acknowledge venting where it exists, you can ascribe real accelerations to imaginary geometry. My own view is simple. Acknowledge the possibility of outgassing forces, test for them, and keep the model restrained until the baseline is long enough to justify finer structure. The ecliptic itself deserves a moment because we invoke it often in this story. It is the plane defined by Earth's orbit around the Sun, and by legacy, we use it as the reference for all orbital inclinations in the solar system. When we say an orbit is close to the ecliptic, we mean that the angle between the object's path and Earth's orbital plane is small. When we say retrograde, we mean that the angle is measured in the opposite sense to the planet's general motion, so the object effectively swims upstream. These two facts can coexist, and here they seem to do so. That coexistence has practical consequences. A path near the plane means more chances for planetary alignments that matter to observers and spacecraft planners. A retrograde sense means high relative speeds when the object passes through the inner system, which helps explain why even a brief photographic glance can show smearing and why timing windows for sharp imaging are narrow. The coordinate language that follows these statements can sound severe. Longitude of the ascending node, argument of perihelion, inclination, perihelion distance. They are simply the 6 numbers that, together with a moment in time, specify an orbit in 3 dimensions. Each has an uncertainty that early on can be large and not always symmetric. Small changes ripple through predicted sky positions weeks, which is why you will see updated ephemerides posted as new observations land. In an open, unbound orbit, the sensitivity to small errors can be greater than in a closed ellipse, if only because the lever arm of a long approach amplifies tiny angular mismeasurements into kilometers of position difference downrange. The cure is the same as always. Get more data from more latitudes with better calibration. Discovery tells us a second important thing, not about the object, but about our instruments. The surveys that found it operate by scanning wide fields with regular cadence, then letting software stitch faint dots into tracks across the nights. That is a triumph of automation and statistics. It is also a lens with preferences. Fast movers can be missed if they streak too far in one exposure. Slow movers can be missed if their displacement is too small compared to the noise. Objects that cross crowded star fields can be lost amid blends and ghosts. And if a visitor arrives from a direction where bright structures in the Milky Way complicate subtraction, even a real target can be buried in residuals until the geometry improves. Selection effects are not a failure. They are a property to be understood. My cautious opinion is that we should treat the apparent neatness of this object's path through the ecliptic with the same humility we apply to any pattern glimpsed through a filter. Some alignments will simply be the ones we are more likely to notice. When the orbit solution matured through mid and late July, 2 calendar markers emerged. The first was a close pass to the orbital domain of Mars in early October. Close here is an astronomer's word. measured in tens of millions of miles. But for cameras in Martian orbit, that relative proximity can be enough to try a shot. The second was a near approach to the Sun in late October, perihelion, when the object would be hot, bright, and, for frustrating geometric reasons, poorly placed for Earth-based telescopes. Earth and Sun would stand in a geometry that puts the object near the solar glare from our line of sight, shrinking the safe observing window to minutes around sunrise and sunset. And even then, the elongation could be too small for most instruments to risk. That double beat, a possible window at Mars, followed by a likely blackout near the Sun, is the heartbeat that will drive the middle chapters of our story. Between those dates, the object does what gravity and sunlight tell it to do. It falls inward, the Sun's pull converting distance into speed, and its motion across the sky grows more urgent each week. For observers, that urgency translates into exposure calculations. Longer exposures gather more photons and thus more signal, but longer exposures also smear a fast target into a thin line, reducing positional accuracy and blurring any structure in the coma. The compromise is to take many short frames and stack them in the object's moving frame, or to pan the telescope to follow the predicted motion. Both tactics require precise ephemerides. If the predicted track is off by a small amount, the stack will dilute the target instead of sharpening it. This is where networked follow-up really matters, with small and large telescopes collaborating across longitudes to keep the solution current. There is an educational pleasure in watching the mathematics of conic sections play out in the sky, the same family of curves that describes the paths of pebbles thrown from Earth ellipses for satellites, parabolas at escape, hyperbolas for the truly free also governs a guest from between the stars. The difference in scale does not change the rules. What does change is our emotional response. Ellipses are familiar and therefore comfortable. Hyperbolas feel dramatic because they deny the possibility of return. I think that feeling is useful, not because it proves anything about origins, but because it reminds us that gravity is a quiet storyteller. If we listen closely and do our sums correctly, it will tell us where a traveler has been and where it is going next, whether or not we like the answer. One might ask whether a hyperbolic fit could be an artifact of outgassing alone, a bound comet given the appearance of freedom by asymmetric jets. That is a fair question. The history of comet studies contains cases where non-gravitational terms matter. The answer in this case lies in the scale of the effect. Vents can perturb perihelion timing, tweak the argument of perihelion, and bias the mean motion over months. They rarely generate the sustained positive energy relative to the Sun required to turn a bound orbit into an unbound one, unless the underlying energy balance is already near the threshold. The early solutions here place the object safely in the regime of the unbound. That conclusion is not a declaration of origin. It is a boundary condition for all other ideas we will explore. As we move from geometry to what this path enables, it is helpful to translate orbital elements into practical observing weather. The near-ecliptic course offers alignments with planetary assets. A retrograde sense raises encounter speeds, which makes any close looks shorter and technically more demanding. The approach to perihelion promises a more active coma and stronger tails, a boon for studying how it sheds its material into the solar wind. But the viewing at that moment will be constrained by glare, safety limits, and the sheer dynamic brightness of the Sun's neighborhood. Those facts are not obstacles to drama. They are the spine of a plan. We accept what cannot be changed and invest attention where the geometry is kind. There is one last bias worth mentioning before we leave this part of the story. Humans are storytellers who like patterns that feel intentional. When an object arrives along a path that seems unusually informative for us, it is natural to ask if that informativeness was by design. I suggest in advance that we anchor our curiosity to the hard parts of the orbit solution, the error bars, and the ways selection and cadence influence what we notice. The line between intention and coincidence is not a philosophical question alone. It is a quantitative one, answered by comparing how often different geometries would be flagged by our current survey systems and how often they would be missed. That is not as romantic as the question invites, but it is how we keep our footing. The discovery, then, gives us a working map. A hyperbolic traveller, retrograde, but close to the ecliptic, inbound toward a late October perihelion, with a brief chance for a closer look near Mars beforehand, and with speed and geometry that make every observing hour count. From that map flow, we will use the practical questions to test ideas. How early did activity begin? And what does that say about the surface and the interior? How do its tails couple to the solar wind as the field geometry changes? Do any electromagnetic signatures track with geometry in ways that favor natural or technological explanations? I am committed to treating each answer as provisional as we gather it, letting the weight of evidence accumulate rather than asking a single moment to carry more than it should. In the next part, we will pull the camera back and place this visitor in a longer lineage. It is not the first traveler we have met between the stars, and it will not be the last. Understanding how we found it, and just as important, how we could have missed it, will help us decide which of today's puzzles are real, and which are shadows cast by our own methods. To understand what a single traveler can teach us, it helps to step back and look at the handful of times we have met wanderers from beyond the sun's family. The record is brief, which is both limiting and precious. With so few examples, every new object pulls more weight than it should in our imagination. But even a short lineage can clarify our questions, and it can reveal how our instruments shape the stories we tell. The modern chapter began with a detection that did not look like a comet at all. In late 2017, survey images from Hawaii revealed a faint, fast point sliding across the starfield. Follow-up photometry showed a brightness pattern that rose and fell as if the object were elongated and tumbling, perhaps shaped like a cigar or a pancake, depending on whose model you favored. There was no obvious coma, no classic fog of ice turning to gas, yet the trajectory was not bound to the sun. That combination forced new language into our nightly briefings. An interstellar object, but not behaving like the comets we knew. Attempts to explain a small, persistent, non-gravitational acceleration without visible outgassing lit a debate that has not fully cooled. Exotic ices were proposed. Surface vents too fine for our instruments to resolve were proposed. Even the possibility of a thin sheet optimized for radiation pressure was proposed. What matters here is not which idea you liked. What matters is the boundary that detection highlighted. Observations limited by geometry, distance, and time leave room where multiple explanations can fit, and our biases rush in to occupy the gap. A couple of years later, the second visitor arrived with less ambiguity. It wore the familiar clothing of a comet. A diffuse coma, a tail, a spectrum with the usual signatures. Its path was open like the first one's, but its behavior was comfortably aligned with what textbooks had trained us to expect. Interstellar, yes, but in the sense that a comet from far away can still be a comet. That detection provided a different kind of boundary. The extraordinary can also look ordinary if you meet it under generous conditions. A visitor need not be strange to be from elsewhere. If the activity begins where the sunlight is warm enough, if the gases are the ones we have catalogued for decades, your doubts about origin are not resolved, but they are quieted. Those two cases set the stage for the object we are following now. One suggested that a traveler can surprise us by how it sheds, spins, or accelerates without leaving obvious clues. The other reminded us that an interstellar origin does not require exotic behavior. The third challenges us by mixing familiarity and strangeness in inconvenient proportions. The orbit is clearly not bound. The path through the solar system is statistically unusual without being impossible. The activity seems to begin earlier than our instincts predict, and the chemistry refuses to sit still in our categories. Put all of that together, and you get a lesson that extends beyond any single hypothesis. Selection matters, cadence matters, geometry matters. In a sample this small, the way we look is almost as important as what is there. It is worth spending a few minutes with the mechanics of how we look. Wide-field surveys rule the modern sky. A telescope stares at a patch, takes an exposure long enough to pull faint points above the noise, then moves to the next patch. Hours later, it returns to the first patch and repeats the process. Software subtracts tonight's image from a reference image and asks a simple question. What changed? Fixed stars subtract away. Cosmic rays, airplane trails, and detector blemishes leave recognizable scars. Moving objects leave clean little dots in different places, or in the case of the faster ones, short streaks. Those detections are then sent to a linking algorithm that decides which dots taken at different times probably belong to the same physical object. That decision is not trivial. The sky is messy, the cadence is not perfectly regular, and objects can be faint near the detection threshold. The linking step, performed well, is the quiet triumph of modern surveys. It turns scattered photons into the beginnings of an orbit. Every choice in that chain has consequences. Exposure length determines how faint a point you can see, but it also determines how much a fast mover will smear into a thin line. A long smear spreads the light across many pixels, reducing the peak signal and making the detection less certain. This is called trailing loss, and it is one reason we are less sensitive to interstellar objects moving swiftly near Earth. The cadence of revisits matters too. If you return too soon, you may not see enough movement to separate a real object from noise. If you return too late, you may find that the object has moved out of your field entirely. Moonlight raises the background brightness and steals faint sources from your catalogue. Clouds do what clouds have always done. Camera defects, saturated stars, and diffraction spikes conspire to hide a small signal where the sky is crowded. None of these is a failure. They are the ordinary texture of looking and the shape of which stories we hear. The sky itself contributes its own preferences. Observers favor regions away from the glare of the sun, both for safety and for practicality. We spend more time near opposition, where an object is opposite the sun in the sky and is up for most of the night. The galactic plane, while beautiful, is dense with stars and nebulosity, which makes subtraction more difficult and raises the background residuals. Near the ecliptic, where most known asteroids live, surveys often schedule more coverage because there is more guaranteed return on investment. Off the ecliptic, especially at high latitudes, the density of known movers is lower, and programs may devote less cadence. An interstellar visitor passing through areas we cover more often is more likely to be found. One sliding through the sun's glare, or the thick band of the Milky Way, is more likely to be missed. If you imagine the sweep of tens of thousands of exposures across months, you can see how a path that seems convenient for discovery might only be convenient for us. These preferences lead to a temptation I try to keep at arm's length. When an object's path aligns with our assets, we sometimes reach for words like optimized or designed. The right way to test that feeling is not with rhetoric, but with arithmetic. Ask how likely a random set of interstellar trajectories would be to cross the regions we canvass most deeply, given our true cadence and sensitivity. Ask how often a visitor would be detectable given its speed, phase angle, and size. Ask how the choice of which frame gets processed first, or which alert system routes a candidate to human eyes faster, changes the time between first light and confident orbit. Somewhere in that accounting is a number that tells you how surprised you are when an object skims the ecliptic or presents itself during months when the weather is kind. Without the number, surprise is only a mood. The smaller sample reminds us to watch our language about typical and unusual. When you have 3 or 4 points drawn from a distribution you do not know, the words ordinary and outlier lose their anchors. One object may look extraordinary simply because the circumstances of its discovery magnified a quirk that would have been invisible under different lighting. Another may look ordinary because our data were generous. It is entirely consistent for a population of interstellar objects to include members that shed early, members that shed late, and members that do not shed in ways we can recognize at all. It is equally consistent for paths to be scattered across a wide range of inclinations and nodes, with a few wandering near the ecliptic by chance alone. If that is true, then the apparent neatness of a path tells us very little about intention, and a great deal about how frequently we sweep that path with our cameras. Consider the phase angle, the sun object observer geometry that governs how bright a dusty object looks. Near opposition, with the sun behind us, a diffuse coma can benefit from an opposition surge, a subtle brightening as shadows on grains vanish. Near small elongations, when the object sits close to the sun in our sky, forward scattering can boost the brightness differently, but those angles are dangerous to observe and often excluded from surveys. As a result, an object can spend weeks in a brightness regime we avoid, then cross into a geometry we favor, and suddenly we call it a fast riser. Nothing changed about the object. Our angle did. When we later say it activated early or late, we should remember how our vantage point can mimic a physical change. There is a complementary effect at work with distance. An object's apparent brightness scales roughly as the inverse square of its distance both from the sun and from Earth. As it falls inward, the sunlight it receives rises, and as it approaches Earth, the light that reaches us suffers less dilution. These two changes combine to steepen the light curve, even if the object's own activity is steady. A person looking only at the brightness might conclude that a switch was thrown. The more patient person folds in geometry and sees a smoother story. When the object is also active, expelling dust and gas that can grow or fade with local surface conditions, the separation between geometric and physical causes becomes harder, which is one reason we avoid strong claims when the baseline is short. All of this is a long way of saying that our tools do not only record the sky, they transform it in predictable ways. The surveys that feed us detections have improved at a pace that would have surprised our predecessors. Pipelines for difference imaging have cut false positives dramatically. Automated stations pass alerts across oceans in seconds. Amateur and professional communities follow up in collaborative bursts that would have been impossible a generation ago. The next wave of facilities will push deeper and faster still. This is a triumph. It is also a reminder to anchor interpretations in the true selection function of the instruments we use. If you do not know what you are less likely to see, you cannot know how odd the things you do see really are. The first two interstellar visitors also taught us a social lesson about how we talk when time is short. When a detection is fresh, adrenaline rises. Claims, counterclaims, and headlines move faster than peer-reviewed pages can. The scientific method still works, but the public rhythm runs on a different clock. If you are trying to keep an even tone, the trick is not to punish curiosity. It is to channel it into testable statements and watch the experiments unfold. In the case of the first visitor, the tests were mostly about whether a non-gravitational acceleration required new physics, new materials, or simply subtler outgassing. In the case of the second, the tests were about whether anything at all about its chemistry or dust distributions fell outside our experience. In our present case, the test will be about ratios that seem extreme, about activity that begins early, and about signals that flirt with patterns. None of these is a reason to leap. There are reasons to look more carefully. Another way to place our current object in context is to ask how often we should expect to find such things at all. Estimates are crude because the sample is so small, but the direction is clear. With surveys scanning more of the sky more often to greater depth, the rate of discovery will rise. That simple fact carries a quiet warning. The first few discoveries in any new regime often feel special because they are the first. As the sample grows, the tails of the distribution fill in and the extremes feel less extreme. We will find visitors that are more active than we thought possible, and others that barely announce themselves at all. We will find ones that pass high above the ecliptic, where few telescopes linger, and ones that happen to scrape the very lanes we sweep nightly. Today's narratives about design may age into tomorrow's footnotes about cadence. That is not a loss. It is growth. The broader picture also sharpens our sense of what a balanced explanation looks like. When a single line of evidence shouts, the safest path is to ask how that line might be contaminated by geometry, noise, or pipeline assumptions. When different lines quietly point in the same direction, you can allow yourself a bit more confidence. In this story, the orbital geometry is secure. The interstellar nature of the path does not rely on delicate assumptions. The unusual aspects lie elsewhere, in the chemistry and in the timing of activity, and in some reports of electromagnetic behavior that have not yet cleared the highest bars. If the object had approached along a steeper inclination, if it had glided past the inner planets when fewer assets were awake, we might be telling the same story without the sense of alignment that colors the conversation now. Recognizing that helps us hold our footing when words like coincidence and intention are thrown across a crowded room. My own position, for what it is worth, is to let the bigger picture discipline the local excitement. We do not need to sand the edges off a good mystery to keep our balance. We only need to remember that instruments are filters and that first impressions in astronomy are often painted by geometry. The previous visitors taught us that our categories are more flexible than we thought. This one may teach us that our expectations about when and how a comet wakes need adjustment, or that some region of formation produces ratios that feel extreme to us only because our catalogue is small. It may teach us nothing's supernatural at all and still enlarge our map of the plausible. There is, finally, a human reason to rehearse these lessons in a single, quiet breath. Wonder is not harmed by accuracy. A traveler from another star system remains a traveler from another star system, even if every quirk finds a natural cause. The scale of the journey, the patience implied by a path that took ages before it brushed our sun, the fact that we can measure any of this with glass and silicon, and a grammar of conic sections written 2 centuries ago, all of that is astonishing enough. If we make room for that kind of wonder, we can ask better questions about the surprising parts without needing them to carry the entire weight of our awe. The larger picture, then, does not dull the edges of our present story. It sharpens them. It separates which clues are robust from which are fragile. It shows us how a survey's cadence can turn a passing lane of the sky into a stage, and how a gap in geometry can silence a moment we most want to hear. With that foundation in place, we can turn to the next layer, the one where light becomes language, spectra replace positions, bands and lines replace ephemerides. We will ask what the object exhales, when it began to do so, and why the balance of its breath leans so hard toward one gas in particular. If the previous parts charted where the traveler is going, the next will ask what it is made of and how it changes as the sun leans closer. Light can be turned into language if you know the alphabet it speaks. For astronomers, that alphabet is spectroscopy, the practice of spreading a source into its colors and reading the thin, dark notches and bright stitches that specific atoms and molecules imprint there. Each species writes its name in a set of lines at characteristic wavelengths. In sunlight reflected off a small body, those names appear faintly, mixed with the spectrum of the sun and with the glow of dust. In emission from a gas cloud around that body, some names shine more clearly. When we say the breath of this traveler leans strongly toward carbon dioxide compared with water, we are summarizing many nights of work that turned streams of photons into ratios, and those ratios into questions. A few basics are worth laying down before we look at what makes this object unusual. A comet is not a single solid thing in any useful observational sense. It is a compact nucleus wrapped, when active, in a loose atmosphere called the coma. The coma forms when sunlight warms ices in or near the surface. Those ices sublime into gas, and that gas drags dust grains into space. The dust reflects sunlight. The gas glows at lines that correspond to its composition, sometimes directly and sometimes through daughter products formed when sunlight breaks molecules apart. Beyond the coma, 2 kinds of tails stretch away. One is a dust tail that roughly follows the orbital path, shaped by the pressure of sunlight on grains. The other is an ion tail, a filament of charged particles guided by the magnetic field carried outward by the solar wind. Taken together, coma, dust tail, and ion tail are a living diagram of energy and flow. When observers speak about water in a comet, they often do not see water directly. Instead, they detect a fragment called OH, a radical produced when sunlight splits water molecules. Measuring OH and accounting for the physics of photodissociation lets you infer how much water is present. Carbon dioxide can be trickier. It does not have strong features in the same wavelengths accessible to the most common ground-based optical spectrographs. Facilities that reach deeper into the infrared or space-based instruments that look where the Earth's atmosphere is less forgiving can pick up the signatures needed. When the lines of carbon dioxide stand out, while the proxies for water barely lift above noise, you begin to suspect that the balance between these two common cometary volatiles is not the one you learned in textbooks. For our current object, that balance appears skewed. The simplest way to say it is that the gas coming off the body contains much more carbon dioxide relative to water than we typically see, and that this imbalance shows up earlier, at larger distances from the sun, than our instincts would have predicted. Early activity matters because it hints at either supervolatiles near the surface or pathways for gas to escape that do not require deep warming. Water ice stays quiet until temperatures climb. Carbon dioxide can wake up farther out. If carbon dioxide is abundant and close to vents, the coma can appear at distances where many comets are still dark. If the source of gas is not only from the immediate skin of the nucleus, but also from embedded reservoirs or even from more complex processes in a porous matrix, the timeline of activity can decouple from simple sunlight curves. There are at least 3 classes of natural explanations to consider before we let the mind wander toward the extraordinary. The first is composition at birth. If this object formed in a region of its native system that favored the trapping of carbon dioxide over water, or if it lost water through past heating while preserving deeper carbon dioxide, then the present coma could be an honest census of what remains. Planet formation is messy. Disks around young stars can show temperature gradients, pressure traps, and chemical partitions that concentrate some ices relative to others. We have barely begun to map those environments, even in our own system. To assume that what we see nearby is universal is to forget how local our experience is. The second class concerns architecture and texture. A nucleus is not a polished rock. It is a complicated assembly of grains and voids, with a skin that evolves under sunlight. If that skin is crusted or sintered in ways that slow the escape of water, but allow carbon dioxide to find its way out through microfractures, you can manufacture an apparent excess of carbon dioxide without requiring a pump that prefers it intrinsically. Think of a snowbank layered with refrozen sleet. The same warmth can release vapor more easily through some channels than others, and the pattern can appear patchy to a distant eye. Vents may open on slopes that see the sun at favorable angles for part of a rotation and then fall into shadow. As the body spins, the on-again, off-again breathing can show up in a light curve, as a modest flicker, and in a spectrum as an average that hides variety. The third class focuses on processes that rearrange ice after formation. Amorphous water ice can trap other volatiles in its structure. As it transforms to a more ordered crystalline state under warming, it can release those trapped gases in spurts. Thermal stress can crack the surface and expose fresher material, creating brief outbursts that bias samples. Micrometeoroid impacts can do the same. In each case, what looks like an unusual mixture might be a transient snapshot taken during a phase change or during the aftermath of a small shock. Over weeks and months, as the sun climbs higher in the object's sky and the thermal wave propagates, the averages can drift. This is one reason observers are careful to specify when and at what distance a ratio was measured. A single number does not describe a season. I find it helpful when ratios sound extreme to ask practical questions about measurement as well as physics. How clean is the separation of lines at the resolution used? How well was the continuum from dust removed? What are the uncertainties from sky background, from telluric absorption in Earth's own atmosphere, and from calibration lamps? If different instruments with different systematics agree, confidence goes up. If line ratios hinge on a narrow wavelength region vulnerable to atmospheric features, caution should grow. In the early weeks of a campaign, when teams are rushing to make the most of a window before geometry closes, some of these checks arrive later than we might like. That is not a flaw. It is a fact of doing science with telescopes that must serve many masters. The right stance, in my view, is to treat bold chemical claims as provisional until multiple methods converge. Early activity is not only about chemistry, it is also about energy and coupling to the environment. When the coma appears far from the sun, the gas expands into a solar wind that is weaker than it is closer in, and the balance between pressure from photons and pressure from charged particles shifts. Ions produced by sunlight can be swept into an ion tail that points roughly away from the sun, but with kinks and rotations that reflect the structure of the heliospheric magnetic field. Dust grains of different sizes respond differently to radiation pressure, with fine grains pushed more easily into curved sheets, while larger grains lag. The overall appearance becomes a moving seismograph of space weather. If a traveler is more active earlier, it can serve as a tracer for changes in the wind that we would otherwise sample only with spacecraft, and only in a few lanes. Labels such as dust-to-gas ratio will appear in notes and preprints during these months. They are proxies for how efficient the vents are at lifting solids, and for how the nucleus responds to the delicate tug of its own outflow. A gas-rich coma generates more drag and a stronger coupling to plasma fields. A dust-heavy coma changes how light scatters and can mask weak gas lines, forcing observers to work harder to separate chemistry from reflection. When the rotation state of the nucleus is unknown, which is common for faint interstellar visitors, the interplay between jets and spin can also drive subtle torques that change the spin over time. Those torques feed back into the activity pattern by altering which regions see the sun at what angles. If you are looking for a single neat story, you will be disappointed. If you are looking for a catalogue of quiet forces with patient consequences, you will be in good company. There is a natural question to ask when an interstellar object looks chemically odd. Could we be seeing not a native mixture but a surface that was altered by some event before arrival? For example, close passages to stars in its past, or exposure to cosmic rays for very long spans, might change the outermost layers in ways that make certain volatiles easier to release when warmed again. A very long journey through cold, low-density space can densify amorphous ice toward crystalline forms in subtle ways. Even within our own system, repeated heating and cooling can bake a surface into a crust that behaves differently from a fresh interior. If the object is old, the first meters we can influence with sunlight now may be the least representative of its deeper bulk. This is not a counsel of despair. It is an invitation to care about how depth matters. Another angle worth keeping on the table is the possibility of extended sources. Sometimes gas detected in the coma does not come directly from vents on the nucleus, but from fragmentation and sublimation of icy grains that were lofted earlier. Those grains can continue to release molecules as they drift, creating a source that is spatially extended and temporally smeared. When observers integrate light over a wide aperture, they may be mixing fresh emissions with older ones. A pattern that looks like a steady ratio from the nucleus might instead be the average of two processes with different time constants. Untangling this requires maps, not just spectra in a single slit. It requires scanning across the coma to see where the signal is strongest and how it falls with distance from the center. The best studies will combine spatial and spectral information to build a more honest portrait. Because the ratio story reaches ears tuned to speculation, I will put my cards on the table. I do not think chemistry alone will carry us into extraordinary territory. An interstellar object with an unusual balance of common volatiles is a challenge to our catalogue and a gift to modelers of formation zones. It invites us to test whether our expectations, based on a small local sample, were parochial. It does not by itself, nudge the door open to non-natural explanations. The safest path is to fold chemistry into a larger ledger. If independent lines of evidence begin to point the same way, if unusual activity patterns line up in time with electromagnetic signatures that repeat when geometry repeats, if the brightness behavior and the gas lines and the tail structures cohere into a pattern that survives attempts to break it, then we will have reason to raise our eyebrows higher. Until then, ratios remain clues, not verdicts. There is one more reason early activity matters beyond composition and physics. It sets the stage for all of the debates that follow by defining when and where the object becomes easiest to see. If the coma forms early, it increases the cross-section for sunlight and can make the target accessible to smaller telescopes sooner. It can also make precise astrometry harder by smearing the point spread function, which affects orbit refinement. It can sway which instruments win time on the schedules of larger observatories, because programs that can advertise a clear target sooner often fare better in competitive rounds. Those scheduling choices feed back into the story the public hears, because they decide which teams can collect which kinds of data and when. In that sense, a carbon dioxide-rich early coma is not just a scientific fact. It is a piece of logistics that shapes the rest of the narrative. All of the above sits in the modest light of caution. Measurements improve, systematics reveal themselves only after arguments have been had and calibration files have been swapped across email. We are watching that process in real time, and if we keep our footing, we will appreciate its pace rather than resenting its carefulness. My own habit is to keep a notebook that tracks which claims have seen confirmation by independent methods and which still hang from a single beam. For chemistry and activity, that means reserving my higher confidence for patterns that persist across instruments and for trends that match simple physical expectations when angles and distances are taken into account. If light can be read for composition, it can also be watched for rhythm. The same campaigns that build a chemical ledger will collect time series that show whether brightness grows smoothly or in steps, and whether the object flickers in a way that repeats with rotation. In the next part, we turn from static spectra to dynamic signals. We will ask how scientists separate meaningful structure from noise in radio and in optical light curves, and how they decide when a pattern is a real voice and when it is only wind on the microphone. Chemistry has given us an early wake-up and an unusual balance. The question now is whether the night sky is whispering in a way that repeats, and what the responsible listener should do when the whisper sounds like a beat. If light gives us chemistry, radio gives us rhythm. The temptation, when you hear that a telescope somewhere registered a brief pulse from the direction of a visitor, is to lean in and wonder whether someone knocked on the door. The discipline is to sit back and ask a smaller set of questions first. What exactly did the instrument record? How did that recording travel through the hardware and software chain? What filters, gains, and flags touched it before a human ever saw it? In radio astronomy, the path from sky to screen is long, and every link can add artifacts that mimic intention. The aim is not to scold curiosity, but to keep it from outrunning the data. Begin with what a deliberately engineered transmission tends to look like. The hallmark in classical searches is unnaturally narrow bandwidth, the energy compressed into a tiny slice of frequency that nature rarely uses. Another is a clean, steady drift in frequency over time, caused by relative motion between transmitter and receiver, and by accelerations at the source. That drift follows the simple Doppler relation, and when you correct the data to the barycenter of the solar system, truly celestial signals maintain a coherent pattern, while local interference does not. Polarization can matter as well. Some transmitters would likely choose a well-defined linear or circular polarization. Natural plasmas produce a variety of polarizations, some randomized by scattering and some set by magnetic fields. None of these indicators is decisive alone. Together, they begin to mark a trail. Now consider the ways the world and our machines imitate those traits. Aircraft and satellites fill the sky with narrow carriers that drift as they move. Some communications constellations hop predictably in and out of bands that ground-based telescopes monitor. Radar side lobes and intermodulation products sprinkle faint copies of strong signals across a spectrum in places that make no physical sense. Digital back-end systems resample and channelize signals into tidy frequency bins that sometimes ring and bleed, drawing false lines that a waterfall plot can mistake for music. Even the act of flagging known radio frequency interference can create holes that make the remaining spectrum look cleaner than it is, and a human eye trained to prefer patterns will color in the gaps. This is why serious searches for technology in the sky do not rely on a single dish watching a single patch once. The standard practice is to nod on and off target, to slew to a nearby sky position with the same elevation and azimuth path, and ask if the signal follows the object or the telescope. It is to run multiple beams simultaneously, one on the target and others slightly off, watching to see if a detection appears everywhere with equal strength, which is the signature of a service satellite passing through all beams rather than a distant point source. It is to record the raw voltage streams where possible so that later generations of algorithms can revisit the event with better filters. It is to coordinate with another facility far away so that local interference cannot fool both instruments in the same way at the same time. When people describe a pulse as mathematical, what they often mean is that the spacing between subpulses appears regular or that the energy is concentrated in tones that fall on simple ratios. But pulsars can be regular in their own right, and magnetars can crackle in ways that repeat with their spin. Solar system spacecraft can transmit with deeply structured modulations that an inattentive pipeline may not fully recognize and remove. The universe delights in patterns, and a responsible listener remembers that before reaching for the label artificial. A useful exercise in these cases is to compute the dispersion measure, the frequency-dependent delay introduced by free electrons along the line of sight. Broadband natural bursts from beyond the solar wind arrive with lower frequencies delayed relative to higher ones in a smooth way. Narrowband engineered tones do not show that sweep, but the computation is only as honest as the bandwidth you have access to, and narrow coverage can trick you into seeing or missing dispersion where it does or does not exist. There is also a local plasma to worry about. Comets couple to the solar wind and generate their own plasma environments with bow shocks and magnetic draping. Those environments can host waves and instabilities that place power into specific frequencies related to the gyro motion of charged particles around field lines. Electric field instruments on spacecraft have detected such waves in situ at comets before. Ground-based radio telescopes, however, receive through Earth's ionosphere and through hardware chains designed primarily for astrophysical continuum or spectral line work, not for the subtleties of plasma wave studies. A spectrum colored by cometary plasma can masquerade as intention if we forget that nature has its own favorite notes. Where would a cautious searcher listen? There is a traditional region near the spin-flip transition of neutral hydrogen at about 1420 MHz, sometimes called the waterhole, because nearby lies a hydroxyl line, and together they form a poetic bracket. It is a quiet patch of sky in radio terms, meaning that the galactic background is relatively low and the atmosphere is forgiving. But it is not empty. Modern communications edge up against old assumptions, and protected bands are not always perfectly quiet in practice. Good work listens widely and then narrows where the evidence and the regulations allow. Good work splits the spectrum into time-frequency tiles and looks not only for single tones, but for chirps that sweep, for binary modulations, for narrow combs of evenly spaced carriers, and for structures that repeat when geometry repeats. Geometry matters because it gives you a lever. If a candidate signal emerges while the object is at a particular phase angle and vanishes when the angle changes, only to return when the angle returns, you gain a clue that is hard for local interference to fake. If a drift rate repeats at the same sky position day after day in the solar system corrected frame, you gain another. If polarization rotates in a way that matches a model of the path through the interplanetary magnetic field, you gain a third. None of these is our trophy. They are breadcrumbs that lead you away from your receivers and toward the sky. A careful program would pair radio with optical and infrared time series. If the light curve shows a periodic flicker plausibly caused by rotation, and if radio structure strengthens when a particular face of the nucleus points sunward, you can test whether outgassing-driven plasma phenomena are enough to explain both. If radio events correlate with solar wind changes measured by monitors elsewhere, and arrive with lags that match propagation times, you have a strong case for an environmental cause. If radio features appear with no regard for the state of the solar wind, with a drift pattern that locks to barycentric correction instead of topocentric time, and with a predictability that recurs across observing runs separated by days and weeks, your eyebrows earn the right to rise a little higher. In these choices lives a larger lesson about extraordinary claims. The easiest path to a headline is a single waterfall plot with a bright streak and a caption written in heat. The hardest path is a month of carefully designed on and off sequences, polarization solutions, beam mapping, and independent confirmation, followed by a measured sentence. I am not romantic about this. The world pays more attention to the first path. But if we are serious about learning rather than thrilling, the second is the only one that matters. The standard for a credible claim is not perfection. It is a pattern of survival against the obvious ways nature and our machines fool us. Suppose for a moment that you adopt the most conservative hypothesis that fits the early hints. You assume that any radio bursts are natural and related to plasma processes in and around the coma and tail. What predictions does that make? You would expect strength and frequency content to correlate with changes in solar wind speed and magnetic field orientation. You would expect events near sector boundaries and co-rotating interaction regions to be more common because those are places where field geometry and density change. You would look for repetition tied not to precise spin phase only, but also to the object's position relative to the heliospheric current sheet. You would be unsurprised by short, impulsive bursts that mirror the sporadic character of reconnection. Some of these expectations are testable with public data streams and coordinated observation campaigns. They make the natural hypothesis vulnerable where it should be. Now, suppose you entertain a technological interpretation long enough to frame a test. You would expect narrow tones or very narrow substructures inside a broader envelope. You would expect a drift consistent with acceleration at the source and with the Earth's motions, not with local equipment drifts. You might expect polarization to be stable in a way that reflects an engineered antenna rather than a wave mode enslaved to a changing magnetic field. You might expect repetition timed to a schedule or a geometric trigger that has more to do with visibility to a preferred line than with solar wind variability. You might even expect non-radio companions, such as flashes in optical light timed in precise sequences that serve no obvious natural purpose. Those expectations likewise create vulnerabilities. If they fail, the extraordinary explanation loses fuel. Between those two poles lies a landscape that contains false positives we have met before. A satellite grazing a telescope's side lobe so faintly that its catalogued identity is missed. A terrestrial transmitter reflected off a meteor trail, appearing to come from above for a few seconds at a time. A bad cable in a signal chain that arcs and produces a comb of evenly spaced lines, whose spacing unfortunately matches some comfortable ratio. Teams that have chased such ghosts carry scars that make them better skeptics. They bled time on ghosts and later built tools to suppress them. You want those teams involved when the next candidate surfaces. You want their checklists in the room. If I sound insistent about caution, it is because the most precious part of a mystery is the chance to design the right measurements before the window closes. A frenzy burns that chance. A plan preserves it. The plan for a case like this is plain. Observe at least 2 facilities separated by large distances. Use on and off pointing and multiple beams. Record raw voltages when possible, and keep the metadata rich enough that later barycentric corrections and polarization solutions can be applied. Share enough information that others can attempt a replication quickly. Fold in optical photometry so that any rotation-linked effects can be tested. Monitor the solar wind and integrate those conditions into your forecasting and retrospective analysis. Above all, publish negative results with the same care you apply to exciting ones. A community that only speaks when the plot looks like a message is a community that will relearn the same lessons every year. There is also the question of patience across timescales. If a signal appears only once and never returns despite superior coverage, you learn something. If it returns at the same geometry, but not at others, you learn something else. If it returns in a way that drifts slowly in time, as the orbit carries the object inward, consistent with changing relative velocities, the case for a celestial origin strengthens. If it returns at the same topocentric time of day, regardless of where the object is, the case for a local source strengthens. Simple bookkeeping about when and where can be more powerful than any exotic model if you let it. I have left aside one seductive habit that harms clear thinking. It is the urge to connect an intriguing radio event to a historical precedent and treat the resemblance as evidence. The resemblance is a story device. Evidence is what survives control experiments and alternative explanations. The right way to honor a famous mystery is not to turn the new thing into its echo, but to design better tests than the old observers had tools to attempt. Our receivers are better now. Our timestamping is more accurate. Our ability to coordinate globally is vastly improved. We can do this part well if we choose to. What, then, would count as a strong case that the radio sky is telling us more than plasma physics? In my book, it would require a narrowband or sparsely modulated signal that repeats with a geometry-driven cadence, that is seen independently by multiple instruments with consistent drift rates once corrected to the same frame, that shows polarization properties stable enough to resist trivial natural explanations, and that either coincides with or is complemented by optical or infrared timing behavior that has no plausible natural synchronizing agent. It would require the boring work of eliminating every known satellite and every plausible reflection path. It would require time in the sky that lets the case grow beyond a single pretty plot. If that sounds like a high bar, it is because we have learned over decades that nothing less will hold. Until such a case is made, the honorable posture is curious but unconvinced. That posture does not dampen wonder. It keeps wonder honest. The night sky is alive with signals, and some of them truly are messages, but most are from our own machines. The ones that are not are produced by plasmas and magnetic fields that, on their own terms, are so rich and dynamic that understanding them can feel like reading a living book. The cometary environment modern instruments can probe is not an empty stage waiting for an actor. It is already a drama of ions and dust and fields. Listening carefully teaches us that before it teaches us anything else. In the next part, we shift our attention from the radio to the eye, from the spectrometer to the camera that watches brightness rise and fall. Reports of optical flicker carry their own risks and their own rewards. Rotation, jets, forward scattering, and instrumental seeing all write their marks into a light curve. If there is a pattern in that flicker, a pattern that survives checks and repeats when geometry repeats, it can be the companion to whatever the radios hear, or it can stand as an independent clue. Either way, the discipline does not change. We will look for rhythm, and we will ask it to survive the simplest ways a mistake could have created it. Brightness is the simplest message the sky can send, and the most easily misunderstood. A light curve looks innocent on the page, a clean line that rises and falls with time, but every point on that line is a small negotiation with physics and with the instrument that gathered it. When reports surfaced of steady, evenly spaced, brightening pulses near our visitor, The claim reached straight for the part of us that wants pattern to mean purpose. The discipline is to ask if rotation, jets, geometry, and our own observing habits can write a rhythm convincing enough to fool a careful ear. Begin with rotation, the most common clock in small body photometry. A bare, elongated nucleus that spins will brighten as its long side turns toward us and dim as its narrow side returns, tracing a double-peaked curve across one rotation. Coma complicates this by adding a constant glow around the nucleus, reducing the amplitude of shape-driven variation and blurring crisp edges in time. Yet rotation can still assert itself when jets are tied to specific longitudes on the surface. As vents rotate into sunlight, they switch on, and as they rotate into night, they fall silent. If the object is in simple principal axis rotation, the resulting light curve can be periodic and stable for days. If it is tumbling in a non-principal axis state, as some comets and small asteroids do, 2 or more periods can interfere to produce beats and patterns that mimic more exotic timing. The distinction is not philosophical. It is measured with a time series long enough to see whether a single period solution holds across nights or whether the phases drift in ways a 2-period model can explain. Jets offer a second, subtler clock. Imagine a fountain of dust and gas anchored near a fissure. Sunlight hits, volatiles erupt, and a sheet of fine particles rises and falls into the coma. The sheet itself is bright only because it reflects sunlight, and its reflectivity depends on the angle between the sun, the object, and the observer, the phase angle. As that angle changes over a night and across weeks, forward scattering can boost the apparent brightness when the dust sits nearly between us and the sun, and it can diminish when the geometry moves away from that sweet spot. The boost is not a pulse train in the strict sense, but when jet output is modulated by rotation and then filtered by phase angle, the combination can produce regular humps that look engineered if you forget how many knobs nature is turning at once. Scattering physics writes its own rules on every grain. Large grains scatter light more like small mirrors, with a milder dependence on wavelength and a narrower lobe of forward scattering. Submicron grains behave more like fog, throwing light broadly and reddening the spectrum. If you watch a target in multiple filters at cadence fast enough to follow a claimed pulse, you can test whether the contrast of the flicker is color dependent. A natural jet-driven effect should show chromaticity that tracks grain size distributions. An engineered optical beacon, if we let the mind wander that far, would be most naturally narrowband and show strong color dependence only near its chosen line. Multiband photometry is not decoration in this regime. It is a lever. The atmosphere above every observatory introduces its own rhythms, and a proper light curve respects them. Scintillation, the twinkling that betrays turbulence, injects noise that scales with telescope aperture, air mass, and exposure length. Transparency drifts as thin cirrus passes. Extinction increases at low elevations where light travels through thicker air. The antidote to these wandering baselines is differential photometry. Measure the target against comparison stars in the same field whose intrinsic variability is negligible. Normalize the target flux to a steady ensemble and let common mode trends subtract away. Add a check star, a second object treated like the target but known to be constant, and demand that its residuals be flat. If the check star shows pseudo-pulses with the same period as the target, the atmosphere or the instrument is speaking more loudly than the comet. Guiding and tracking errors turns stellar images into small teardrops or lines. For moving targets, we often track at the comet's predicted rate, so that the nucleus and inner coma stand still on the detector while field stars streak. Aperture photometry using circular apertures then picks up a coma gradient that can tilt the measured flux as the centering algorithm dances with noise. Point spread function fitting photometry, though powerful for stars, is less perfect when the core is embedded in extended light. A practical compromise is to test multiple apertures and annuli. Measure the sensitivity of the light curve to aperture choice, and report only features that survive those changes. If a neat series of pulses flips sign or vanishes when the aperture expands slightly, the pattern likely lives in how the coma brightness falls with radius rather than in the nucleus itself. Sampling itself can paint a false structure. If you observe with a cadence that resonates with the true rotation period, you can undersample a smooth variation and generate an alias that looks like sudden steps. Regular breaks for meridian flips on a German equatorial mount, or for low elevation avoidance. Sprinkle gaps that a periodogram can interpret as harmonics and subharmonics. The cure is to mix cadences, observe from two longitudes when possible, and use tools designed for uneven time series, Lomskagel periodograms, phase dispersion minimization, and wavelet analysis each bring their own strengths. None should be allowed to declare victory alone. It is the consensus of methods and the stability of a period across data subsets that earns belief. Longer exposures to gather more light introduce trailing losses when you track the stars instead of the comet. Trail targets smear into thin lines, diluting peak flux and mixing the nucleus with more coma. Shorter exposures reduce this, but raise read noise and overhead. Some teams defocus slightly to spread the light over many pixels, reducing scintillation and flat field noise at the cost of resolution. Defocus can help if the method is consistent across the target and check stars, and if the field is not crowded. In a busy star field near the galactic plane, defocus can blend sources and introduce slow beats as the seeing changes. That beat can masquerade as a slow modulation in the target if you do not inspect the subtracted backgrounds. The point is not to ban techniques. It is to insist that a claimed pulse survive reasonable changes in technique. Rotation-tied jets can leave fingerprints other than photometric pulses. In long, deep exposures, corkscrew features sometimes appear in the dust tail as the jet direction sweeps through space with spin. Time sequences of such images can let you infer the rotation period independently, then compare that to the period derived from photometry. Agreement across methods is a strong indicator that you are measuring a real physical clock. Disagreement does not automatically indict the clock. It may mean that the photometry is sensitive to a subharmonic, or to a facet of the surface that comes into sunlight twice per rotation. The honest path is to lay the evidence side by side and let the simpler explanation win. A brightness rhythm that would push us toward extraordinary interpretations has to clear a high bar. It would need to show pulse timing that is strictly regular over windows, longer than any plausible rotation stabilization timescale. It would need to appear in multiple passbands, with a color signature, inconsistent with dust scattering and consistent with a narrowband source. It would need to repeat when geometry repeats and vanish when geometry does not, in a way that locks to barycentric corrections rather than to local clocks. It would need to survive differential photometry with multiple, independent ensembles across instruments separated by geography and design. It would ideally be accompanied by polarization changes that do not track scattering angle, and by a slight spectral structure in the pulses that cannot be dismissed as atmospheric or instrumental. Expectations this strict are not a way to smother drama. They are the way to protect it from collapsing under its own weight. Suppose instead we find a more human story in the data, short sequences of brightenings that are regular on one night but not on another, periods that wander a few percent as the jet that dominates one week yields to a different active region the next. Color changes that grow stronger as the phase angle narrows and then fade as it widens. A correlation between pulse contrast and solar wind conditions measured by spacecraft elsewhere in the inner system. That mixture would favor the natural explanation. It would tell us that we are watching an active surface catch sunlight on a moving machine of its own making, a rotation state, coupled to outgassing and torque and a delicate play between dust sizes and scattering angles. In that explanation, there is still poetry enough. There are practical steps any campaign can take to give the light every chance to speak clearly. Observe in at least 2 filters interleaved within minutes so that color behavior can be tracked, not inferred. Tie exposures to GPS discipline timing and record absolute times at mid-exposure, not at start or end. Use consistent apertures expressed in kilometers at the comet, not only in arcs, seconds on the detector, so that comparisons across nights at different geocentric distances are meaningful. Scatter comparison stars across the field to guard against flat field gradients, and refresh the ensemble if a star shows hidden variability. Rotate the camera or change the dither pattern to ensure that a feature is not locked to a row or column defect. Publish the raw light curves with enough metadata that others can recompute periodograms and test alternative detrendings. Most of all, collaborate across longitudes so that the window of coverage widens and aliasing starves. One often overlooked test is phase folding against geometry rather than time. If a feature appears whenever the solar phase angle sits in a narrow band, independent of the nominal rotation phase, you may be looking at forward scattering through a preferred grain size, rather than at an engine pulsing in the dark. If a feature appears at the same object's Sun-Earth angle and at the same projected jet position angle on the sky, even as the calendar date and hour change, that is a specific, natural key. Conversely, if narrow pulses recur with delays that match neither rotation nor any known scattering enhancement, and keep time in the solar system corrected frame like a clock would, you are obliged to pay attention. The way we choose exposure times carries its own subtle trap. Short exposures reduce trailing and preserve time resolution, but they impose a cadence that is often a simple round number, 10 seconds, 20, 30. Those cadences can lock you into harmonics that a period search tool will happily declare significant because they reflect the observing pattern more than the sky. An easy hedge is to jitter the cadence slightly so that the sampling window does not inject a strong spectral comb into the data. It feels untidy to the scheduler. It is healthy for the analysis. My own view is that the story of optical flicker will likely resolve into the same pair of lessons that rule most comet photometry. First, rotation matters, and because shape and vent placement matter, the light curve will be periodic enough to tempt us and messy enough to punish haste. Second, geometry matters, and phase angle, air mass, and seeing must be baked into any claim of pulses that mean more than activity. If there is anything truly startling hidden in the brightness rhythm, it will announce itself by surviving the most boring tests we can devise. There is a final piece to this chapter that we should not ignore. Visual behavior near the sun is where forward scattering peaks, and where instrumental safety often forbids watching. If an optical rhythm grows stronger at small elongations, we will be least equipped to judge it just when it rises, and that absence will tempt the overconfident to fill the gap with certainty. The right response is to say plainly where our reach ends, and to plan how to bridge it with spacecraft, or with ground-based twilight programs that accept narrow windows under careful constraints. We will need that clarity in the days around perihelion. All of this brings us to the next turn in the story, where geometry and logistics, rather than physics alone, decide what we can know. The approach to the sun promises more activity, richer tales, and perhaps cleaner rhythms. But it also forces our instruments to look into glare, to schedule around safety limits, and to live with telemetry gaps that the public will be quick to narrate. In the next part, we will talk about that narrow corridor of observation, why feeds sometimes go dark at the worst moment, and how to separate the ordinary constraints of solar observing from the feeling that something is being withheld. The stretch of sky nearest the sun is where comets often reveal the most, and where we, frustratingly, see the least. The physics is simple. As a small body dives inward, it warms, vents more vigorously, and drags larger clouds of dust and gas into space. Tails sharpen, ion structures respond more strongly to the solar wind. Any subtle periodicities tied to rotation can be amplified by forward scattering, the way fog can glare around a headlight. The logistics are not simple. Telescopes on the ground, and instruments in space are designed to avoid the sun for their own survival, to ration data rates, and to protect detectors from saturation and radiation storms. The result is a corridor of observation that is narrow by design, exactly when curiosity is widest. On Earth, the obstacle has a clear name. Solar elongation is the angle between the sun and your target in the sky. Most optical telescopes impose a strict minimum elongation, often dozens of degrees, to prevent sunlight from entering the optics, heating structures, and flooding detectors with scattered light. Even when a facility allows observations close to dawn or dusk, the bright sky raises the background so high that faint, diffuse comets and thin tails disappear into noise. Twilight offers a sliver of time when the angle is marginally acceptable and the object is still above the horizon. That sliver can amount to minutes, and weather can erase those minutes without apology. You can plan a month for a single 10-minute look and return with nothing more than a log entry and a sigh. Coronagraphs exist to look near the sun without burning out their eyes. They use an internal disk to block the solar disk and suppress scattered light, revealing the inner corona and anything bright enough to stand out near it. Spacecraft like SOHO with its LASCO instruments and the STEREO spacecraft, when geometry cooperates, have shown comets and sun-grazers flaring and disintegrating in that harsh environment. But coronagraphs are not magic eyes. The blocking disk creates an occulting geometry that hides a central region entirely. The remaining field is bathed in a sea of coronal structure, whose brightness and texture change with solar activity. Exposure settings, cadence, and compression are tuned for coronal science, not for chasing a modest interstellar traveler. A small object can be present and simply be invisible to the instrument's intended dynamic range. When you view a coronagraph movie and see nothing where you hoped for something, you may be looking at the limits of design, not the presence of absence. Space telescopes that study the sun itself, such as SDO, and heliophysics missions like Parker Solar Probe or Solar Orbiter, contend with an environment that gets less forgiving during solar maximum. Radiation storms trip protective modes. High-rate telemetry must be budgeted across instruments. Momentum wheels saturate and require desaturation maneuvers that change pointing. Onboard storage is finite, so data are prioritized, downlinked in chunks, and sometimes filtered for compression artifacts that an outsider mistakes for editing. The public sees the gaps and stitches and sometimes calls them silence. Engineers see a vehicle riding the weather of a star and keeping its promises under load. It helps to follow a single image from sky to screen to see how delays and gaps arise. Raw frames leaving a detector are not pretty. They carry bias patterns from electronics, hot pixels, cosmetic defects, and cosmic ray hits. They pass through calibrations derived from dark frames and flats, then through cosmic ray rejection, then through geometric corrections, then through pipeline steps that align frames to a stable reference and subtract backgrounds. Regional masks may be applied to block unreadable portions. Timestamps and pointing data are woven in. If the mission has both real-time and delayed downlink paths, a low-resolution browse product may appear first, while the high-resolution science frames trickle down hours later. If you are watching a live page and see a gap, it could be a simple handoff from one path to the other. The quiet does not imply that nothing was recorded. It often implies that a better product is not ready yet. Sometimes there really is nothing recorded, and the reason is unremarkable. High-gain antennas must point toward Earth for data to flow. When geometry forces a spacecraft to roll to protect radiators or to keep the sun in a safe quadrant of the field, downlink pauses. Ground stations schedule time with many missions, and a deep space network antenna cannot serve two customers at once. Anomalies trip safing protocols that suspend instruments until health checks are complete. Schedulers juggle these constraints and write plans that look like crosswords. During a perihelion week, the crossword gets dense, and a few squares remain blank because they must. Public unease has a calendar of its own. A feed that goes dark as a comet approaches its hottest moment tempts a tidy story. A spacecraft that rotates out of downlink just as chatter rises about optical flicker invites a narrative of intent. The cure is not a lecture about patience. It is a plain accounting of what the vehicle was obliged to do, when it did it, and how the planned gaps align with what the audience saw. Missions that publish operations notes, image latency timelines, and data quality flags earn trust that pays dividends when speculation runs ahead of fact. In that spirit, an astronomer's most constructive sentence can be short. The window was narrow. For this reason, the pipeline needed these hours, and the gap is ordinary. Ground-based networks face a parallel set of ordinary difficulties that look suspicious from far away. A small elongation target sits close to rooftops and mountains. The line of sight crosses long columns of thick air. Refraction shifts and smears images. Adaptive optics that work wonders on bright, compact objects struggle on diffuse comets without clean guide stars. Hour angle limits on mounts trigger meridian flips, forcing a pause just when the target passes through its brightest geometry. Observatories that keep staff and instruments safe will choose to protect hardware rather than gamble a scope's future on a risky attempt near the sun. A no is not an admission of fear. It is simple prudence. Even when a facility says yes, twilight imposes cadence math that produces irregular time series. You may get a handful of short exposures while the sky is viable, then lose the target to trees or buildings, or the horizon before a second cycle completes. Period searches on such sparse data should carry warnings in large type. A rhythm that fits 7 points across 12 minutes is not a drumbeat. It is an invitation to try again tomorrow if the weather permits and the geometry repetitions align. In near-sun work, repetitions are precious. Each day, the elongation and phase angle change, so a reattempt is not a simple do-over. It is a different experiment. Radiation and saturation inside instruments conspire online with the artifact category we call cosmic rays. High-energy particles strike detectors and leave single-frame streaks and blooms that resemble narrow beacons when compressed or when viewed in isolation in a newsfeed. Proper reduction rejects most of these easily, but quick-look products sometimes let them pass, so that scientists can preview a scene for promising features. When a gallery presents those quick looks, viewers can misread a cosmic ray as a signal. The remedy is not to scold the audience. The remedy is to label quick looks and to circle back with cleaned products that show what survived and what did not. One element that deserves candid explanation is the interplay between dynamic range and compression. Instruments tuned for coronal features suppress low-contrast, diffuse structures near the occulta and clip very bright events to preserve detail elsewhere. Telemetry limits encourage lossy compression schemes that throw away information in benign regions to preserve it where the science team expects value. A small, faint object that wanders through a region the onboard compressor considers safe to simplify can be hurt twice, first by design and then by compression. If later processing restores a hint of it in a difference image, some will ask why it was invisible before. The honest answer is that the instrument gave up contrast to save bits in a field dominated by the sun's atmosphere, which is exactly what it was designed to do. All of these operational truths accumulate into a single social fact. The near-sun window is a natural amplifier for speculation because timing and scarcity are story fuel. The way to keep the story anchored is to bring the audience behind the curtain. Explain that elongation limits are written into software and interlocks, that shutters close automatically when a limit is crossed, that operators sign off on plans that include safe holds and calibration sequences, and that no one flips a switch to hide a comet. Explain that negative results are results, that blank frames tell you a tail was below detection at that cadence, and bandpass given the background, and that this also constrains models in ways that matter. In other words, pull mystery toward the side of craft rather than toward the side of plot. There is also value in acknowledging how geometry makes even good faith efforts feel unlucky. In our case, perihelion arrives when Earth sits on the wrong side of the Sun, putting the object close to glare from every sensible vantage. That is not intentional evasiveness. It is a calendar page set by celestial mechanics. A traveler on a long hyperbolic path does not know we exist. It obeys angles and energies. The appearance of avoidance is an illusion created by our seat at the table. Naming that illusion does not erase the frustration. It gives the frustration an honest shape. My own view, shaped by years of watching the quiet parts of the sky with instruments that fail gracefully under stress, is that the best defense against unfounded intrigue is to publish the mundane. Share the schedules. Share the safing logs. Share the lists of when a downlink dish was busy and when it was not. Share the figures of merit that lead a team to choose one exposure time over another near the threshold of saturation. When people can see the scaffolding, they are less tempted to imagine hidden rooms behind the stage. And when a real anomaly appears, the contrast against everyday practice is sharper and easier to respect. None of this is to ask the audience to surrender skepticism. It is to calibrate it. When a data gap aligns with a moment of expected drama, ask whether the gap had to happen for prosaic reasons and whether other instruments were watching elsewhere. When a highlight reel shows a neat dip or flash, ask whether that feature survives in the cleaned product and whether it repeats at the same geometry on a different night. When a claim of blackout bounces across channels, ask to see the operations plan for that week. The answers will often be boring, and that boredom is a friend of truth. There is one more reason to spend time here before we move on. The corridor near the Sun is not only a test of hardware, it is a test of temperament. Teams must decide how to spend scarce minutes of twilight and scarce hours of downlink. They must weigh the odds that a faint interstellar visitor will show something the instrument was not designed to catch, against the certainty that planned coronal campaigns serve large communities. It is legitimate to argue for flexibility during rare events. It is also legitimate for instrument leads to protect baselines that have paid scientific dividends for years. Those choices look like a conspiracy only to those who have not had to make them. To those who have, it looks like stewardship. The days around perihelion will pass, whether our feeds are steady or not. The object will round its tightest approach and emerge into elongations friendlier to ground-based eyes. Ejecta that could not be seen in glare may appear as the sky darkens. Fragmentation, if it occurred, will announce itself in the geometry of condensed knots and the behavior of tail structures. The ledger will grow again with ordinary hours and the kind of data that survives peer review and time. That is when we can ask whether the rhythms hinted at before perihelion were real, whether the chemistry evolves as distance grows, and whether any electromagnetic whispers return when the geometry repeats. From here, the story naturally turns toward an idea that feeds both skepticism and wonder. When a path and a set of observing windows feel unusually generous to our instruments, does that generosity mean anything beyond coincidence? Could a traveler's motion look engineered simply because it intersects our most watched lanes? Or, if we let ourselves ask the immodest question, is there a way to separate the feeling of design from the mathematics of chance? In the next part, we will take that question seriously. We will treat visibility as a measurable quantity, examine how selection bias paints our maps, and ask what a pattern of optimal encounters would look like if it were only the artifact of how we search. Only after that arithmetic is done will we consider what it would take for motion to carry a message. There is a neat seduction in the way this visitor moves. It glides near the ecliptic where our cameras are most awake, slips into a calendar that hands us a Martian vantage before perihelion, and then disappears into glare just when everyone wants a final word. To a storyteller, that sequence feels arranged. To an observer, it feels like geometry. The task here is to weigh those feelings with arithmetic and to ask whether behavior that seems optimized for our attention is anything more than a byproduct of how we look. Begin with a simple definition. Visibility is not a mood. It is a measurable quantity that folds together sky brightness, phase angle, distance, a telescope's sensitivity, and the size and activity of the target. If you compute a visibility field over the sky for a given night and overlay the actual track of the object, you can assign a number to how fortuitous the alignment is. If you repeat that exercise for many hypothetical interstellar paths, drawn from a sensible distribution of directions and speeds, you can learn how often a random traveler would have looked as cooperative as this one. That is the heart of the selection bias problem. Without the denominator, the story will always feel special. Selection enters at every door. Surveys dwell longer near the ecliptic because that is where most asteroids live and where a program can guarantee a full harvest. Weather patterns favor some longitudes and seasons over others, so cadences spike when nights are long and skies are dry. Twilight programs nibble the edges of solar elongation, but rarely risk the inner few degrees where scattered light wins. The galactic plane, gorgeous and inconvenient, hides faint movers in a snow of stars. An interstellar path that hugs the ecliptic, passes through easy weather, and keeps its distance from the Milky Way's bright lanes will naturally drop into more frames, trigger more follow-up, and feel more present in our lives. The feeling of intent is carried along by our own habits. There is a second layer. The pipelines that turn images into candidate tracks are tuned by teams who must manage false positives. If you relax thresholds, the alert stream floods with ghosts. If you tighten them, you miss the faint and the fast. Each survey calibrates these dials to match its telescope, camera, and mission. It is noble work, but it means that the sky we see is already filtered through many small choices. A path that happens to produce short, crisp streaks at the cadence, and typical seeing of a given survey will be linked into a tracklet more easily than one that smears or pauses near chip gaps. That is not cunning from the sky, it is ergonomics. This is why claims of optimized motion deserve a test that respects the machinery. You can simulate interstellar trajectories with a distribution of directions relative to the solar apex and with a spread of speeds typical for stars near the sun. You can then propagate those paths through an observing simulator that knows when each survey looks where, how deep it reaches under moonlight, how long it typically exposes, how often it returns, and how its software links detections. You can ask a clean question. Among the synthetic visitors that appeared in the last 5 years of simulated schedules, how many would have earned as many detections as ours, and how many would have missed perihelion coverage for the same geometric reasons? If the answer is that a few percent look as kind as this one, and a few percent go dark near the sun for similar reasons, then the story of optimization loses its edge and becomes another example of how probability groups events into clusters that feel meaningful to us. Astrometry is the quiet backbone of any such attempt. You cannot stack frames in the object's moving frame unless you know the motion vector accurately, and unless your star positions are precise enough to solve for pointing jumps between frames. This is where deep catalogues of star positions and proper motions earn their keep. A field solution with many stars scattered across the frame lets you remove distortions and match scale and rotation frame to frame. Once that solution holds, you can pivot the entire dataset into the object's coordinate system, align on its centroid, and ask the low contrast coma to reveal itself in the summed image. You can also measure the object's position relative to the background to a fraction of a pixel and improve the overall orbit solution even if the image is not pretty. A detection that looks unimpressive to the eye can still sharpen ephemerides meaningfully. A campaign designed for beauty can still give the numbers their due. The instrument mix on Mars offers more than one way to try. High-resolution images built for geology give you small pixels, and strict control of smear when the target is a cliff or dune. Medium-resolution context cameras give you wider fields and often more forgiving dynamic ranges. Weather instruments with wide-angle cameras can sweep large fields for moving points. None of these were built to chase star-like targets, but each has a domain where it can contribute. The trick is to choreograph them. Let the wide-angle instruments search first with a fast cadence and rough pointing to confirm the track. Let the context camera lock the field and provide stars for registration. Then task the high-resolution camera for the short, sharp exposures that can place a single pixel above the noise. Sharing timestamps and pointing history across teams prevents one instrument from wasting time repairing what another already knows. If we are lucky enough to detect the object as a point source, the next question is whether any asymmetry survives scrutiny. A star is symmetric in a well-behaved point spread function. A small coma superposed on that point can produce subtle wings that fall more slowly with radius than the point spread predicts. By azimuthally averaging the radial profile of the target and comparing it to nearby stars in the same frame, you can look for that excess. If the excess is real, you can translate it into a crude measure of dust production. If the profile matches stars cleanly, you can place upper limits on coma brightness and, by extension, on activity at that distance from the sun. Either result tightens the story. Either result is instructive. A stronger detection opens more doors. If the coma is resolved at all, the direction and curvature of any tail can be measured, and those directions can be compared to syndonies and synchrones. These are curves that model where dust of a given size released at a given time would appear under solar gravity and radiation pressure. When geometry allows, fitting tail shapes can give you an estimate of when major outgassing events occurred and what sizes of grains dominate. Doing this from Mars as well as from Earth adds a priceless second vantage. Stereo in space is not only for landscapes. Two different phase angles and two different lines of sight can disentangle overlapping structures that would otherwise blend in a single projection. The math is not complicated. The logistics are. Some things can go wrong that have nothing to do with the science. Spacecraft must ration data volume. High-resolution images carry big files. Downlink contracts with ground stations are written weeks in advance. If a campaign asks for 100 frames and wins time for 20, the exposure ladder compresses and the confidence intervals expand. Attitude, control, and pointing stability have tolerances that surface. Imaging tolerates better than star imaging. A flutter that blurs nothing on a canyon wall can make a point source swim. Thermal limits keep some pointing maneuvers off the table. Safe mode responses to radiation spikes take instruments down for hours at a time. None of these is malicious. They are the daily weather of spacecraft life. When planning takes them into account up front, expectations stay honest. Now consider outcomes and what they would mean. The best case is a clean point detection with a profile that shows a measurable coma and a faint tail at a consistent position angle across frames. That gives us a flux we can calibrate and compare to Earth-based measurements at nearly the same time. The color, if two filters were used, can be compared to expected dust colors. The tail direction, combined with Mars and Sun geometry, helps constrain what the nucleus was doing in the days leading up to the pass. The second best case is a point detection that matches star profiles. It may feel disappointing, but it is powerful. You can translate the absence of detectable coma into upper limits on dust production. You can also extract an accurate position to feed back into the orbit. When perihelion complicates ground-based work, a single precise point can be gold for trajectory predictions later on. A weaker but still valuable case is a marginal detection in stacks only, with low signal-to-noise. If the signal appears at the predicted location in multiple independent stacks with different subsets of frames, and if it vanishes when you misalign the frames intentionally, you can have reasonable confidence that you have the target. You lose any hope of measuring a profile or a color, but you keep a position. The least satisfying case is a non-detection. Even that is not empty. If the observing plan was deep enough that a typical cometary coma would have been visible, a non-detection tells you that activity was below that threshold at that time, and geometry. It also tells you to adjust expectations for perihelion emergence. In every case, the honest reporting of limits, cadences, and backgrounds protects the rest of the story from the temptation to infer too much. There is a quiet bonus baked into any orbital attempt. Parallax between Mars and Earth during the days of the pass gives us a baseline for 3D reconstruction. If a feature in the tail looks offset relative to the nucleus from both vantage points, you can triangulate its distance from the nucleus. If an outburst occurred, the time since ejection inferred from tail modeling can be cross-checked against that distance and against the relative motion of the dust under solar pressure. This is not only satisfying physics, it is a way to catch errors that single vantage fits can hide. Redundancy is how fragile inferences survive. Another often overlooked channel is photometry through filters that span telltale gas bands. Even if we cannot obtain spectra from Mars' orbit, pushing a camera through a pair of filters, one that lands on a gas emission band and one that samples continuum, can hint at gas-to-dust balance changes. The sign will be noisy. The method is crude compared to a spectrograph. But if the trend repeats on 2 nights, and if it aligns with what Earth-based facilities see in narrowband filters tuned to classic cometary species, you gain a low-resolution chemical timeline that stitches the 2 vantage points together. That timeline, layered over the light curve and the tail morphology, is how a narrative gains muscle. What of interpretation risk? It is easy to imagine more from a single sharp frame than the physics supports. A speck of hot pixel residual, a cosmic ray missed by the filter, or a glint from a bright star streaking through the edge of the field can masquerade as an asymmetry if the viewer is hungry. This is where discipline and checklists matter. Require the feature to appear in more than one frame. Require it to align with geometry in a way that a glint would not. Require it to survive a reprocessing with different background models. The right skepticism does not kill discovery. It preserves it. My own sense of what success looks like is modest and concrete. A positive detection from Mars' orbit that gives a clean astrometric point, an upper limit or measurement on a coma profile, and a tail direction if present, reported with exposure times, pointing histories, and noise estimates transparent enough for others to reweigh, is a triumph. It will not settle grand questions alone. It will tighten the chemistry and activity timeline. It will inform models that ask why carbon dioxide dominated early and whether the ratio evolves as isolation climbs. It will give radio and optical time series watchers something firmer to align to as they search for rhythm. It will be a brick in a patient's wall. Whatever the outcome, the Martian window teaches a lesson we will carry into the next part. When the sky gives a chance that is merely decent, not spectacular, the choice is ours to make it count. That choice is a blend of logistics, engineering, and restraint. It is also a taste of a bolder idea that hovers beyond simple imaging. If a brief encounter at Mars can sharpen our questions, could a deliberate high-speed flyby by a repurposed spacecraft sharpen them further? What would it mean to ask a craft, already busy with its own primary mission, to alter course for one last dash past an interstellar traveler? How would the math of trajectories, fuel margins, and instrument limits support or reject that urge? In the next part, we will shift from cameras perched above a planet to the calculus of retargeting a deep space machine, and we will ask what is possible, what is wise, and how to make sure the desire for a close look does not outrun the responsibility to steward the tools we already have. The urge is familiar. A rare traveler is in the neighborhood, and somewhere in deep space, a sturdy spacecraft is still awake, years past its original goals, its instruments healthy, its antenna whispering across millions of miles. What if we asked that craft to pivot, pick up a little speed from a planet, and fling itself toward a high-speed flyby? The picture is vivid. A camera snaps a handful of frames that shrink guesswork into measurement. A radio experiment weighs the visitor by the way it tugs on the spacecraft's velocity. A spectrometer takes one clean breath as the coma sweeps by. The desire is understandable. The math is stern. Turning that picture into a plan demands more than appetite. It demands a ledger of forces, fuels, risks, and ethics. Begin with the simplest number in interplanetary travel. Delta 5 is the change in velocity a spacecraft can deliver, an accounting of how much the vehicle can speed up, slow down, or change direction by burning the propellant it has left. Every maneuver you ask for spends from that account. Missions that survive beyond their prime learn to treat delta V as a currency. They save a little for safety and fault recovery. They save a little for late discoveries. They save a little for end-of-life disposal that keeps the planet safe from accidental contamination. When someone proposes an intercept, the first question from navigation is not whether it is exciting. It is how many meters per second it costs and what the balance is now. Gravity assists can stretch that balance. A pass behind a planet relative to its motion can bend a trajectory and add speed without burning much propellant. But assists are not magic. The geometry must be right, the timing tight, and the chosen path must not break the mission's rules for radiation exposure, sunlight angles, or occultations. A craft skimming a giant planet's radiation belts for a slingshot may pay a price in noise, degraded detectors, or even mission-ending damage. A craft in a polar orbit around a planet may not be free to leave that orbit at all without more delta V than it can muster. The phrase, "one last dash," hides a library of constraints. Good plans respect the library. Relative velocity at the intercept sets the technical difficulty of the science. The visitor's hyperbolic approach makes an encounter fast by default. Tens of kilometers each second is the regime to expect. At those speeds, a camera has milliseconds before motion smears a point across a pixel. You can shorten exposures to freeze the motion, but you starve the detector of photons and drown faint signals in red noise. You can track the line of sight rate to keep the target still, but guidance and control systems have finite bandwidth. Pointing errors that are trivial for landscapes become fatal for star-like targets. The solution is usually a ladder, short exposures to catch the core, longer ones to hunt the coma, and a plan to stack in the target's frame after the fact if guidance was crisp. Even then, the number of images will be small, the illumination geometry improvised, and the chance of a clean look something you can only raise, never guarantee. Science teams dream in instruments. What would you point at a visitor to discriminate between a comfortable natural story and its more provocative alternatives? A visible and near-infrared spectrometer would read the balance of common volatiles and test whether the carbon dioxide favored earlier remains dominant at closer solar distances. A thermal infrared imager would watch for a hot, smooth surface, unlike a dusty crust, and for temperature changes that track rotation in ways incompatible with a porous body. A polarimeter would measure how light scatters off the coma and off the nucleus at different angles, a sensitive way to distinguish grain sizes and textures. A dust counter would count and size impacts as the craft passes through the outer coma, turning the risk that dust poses into data. A radio science experiment would use the spacecraft's downlink as a precision clock, watching for tiny changes in frequency that betray a gravity field tug. That tug, if it is measurable, can set limits on mass and therefore on bulk density. A nucleus too dense or too light would press the debate in clear ways. These are not hypotheticals. They are experiments with playbooks tested elsewhere. The hitch is that the instruments on any given spacecraft were not designed for this specific job. They need the right angles, the right integration times, and the right thermal and power budgets. You do not get to redesign a camera in cruise. Communications take their own seat at the table. A high-gain antenna must point toward Earth for data to flow at useful rates. A camera prefers to point toward the target. Some spacecraft designs allow both by mounting instruments on a gimbal or by scheduling brief snaps between long downlink stretches. Others demand a choice, look and store now, or point and downlink later. Downlink is not only a matter of radio range, it is scheduled time on the ground antennas that serve many missions. You can ask the network for extra passes to support a rare event. You cannot ask it to forget its other customers. Planning an intercept, therefore, involves not only a trajectory, but a communications campaign, with risk buy-down if a safing event eats a reserved pass, and with honest estimates of how many raw frames you can bring home before the window closes. Navigation lives in the background until it does not. At high speed, a small pointing error projects to a large miss in the sky. Star trackers that keep a spacecraft-oriented lock onto known stars. A field rich enough to guide on, while the target is in view, may not be available along the path you want. Stray light from the sun can contaminate guiders near small elongations. Thermal flexure can bend the alignment just enough to blur a scene. The mitigation is rehearsal. Teams run flight-like simulations using real star fields. They inject noise into models of the control loops. They plan contingency slews and fallback modes. They ask what happens if the first try misses, and whether a second pass at a lower ambition can still yield something. The difference between a graceful miss and a graceful salvage is decided months before you light a thruster. Risk belongs not only to the mission that would be repurposed, it belongs to the assets the mission was designed to serve. A craft keeping vigil over a giant planet's polar regions is not idle when we look away. It is doing hard work for communities that have waited years for that data. A change in orbit to chase a visitor carries an opportunity cost. It can push a planned campaign into a season where geometry is worse. It can raise noise on instruments by nudging the craft into harsher radiation. It can impose thermal cycles that age hardware faster. Principal investigators and project scientists must weigh the gain in one ledger against the loss in another, and their duty is to the mission's charter as well as to serendipity. The glamorous option is not always the responsible one. Planetary protection and end-of-life plans set boundaries too. Many missions commit to specific disposal maneuvers at the end of operations to avoid accidental impact with a world that might harbor or be studied for life. Spending propellant now narrows the route to a safe goodbye later. Engineers can sharpen the pencil and find efficiencies. Nature owns the final say. A mission that cannot guarantee a safe disposal at the end, if it spends a tempting fraction of its propellant now, may have to decline an intercept on those grounds alone. That answer disappoints the imagination. It protects the future. Dust is the most literal risk. High-speed grains carry energies that scale with the square of relative velocity. A craft skimming the faint outer coma may encounter a population of particles that look harmless on paper and still chip optics or scar solar arrays. Some vehicles carry Whipple shields, layered bumpers that spread the energy of an impact. Most do not. If an intercept would drive a craft through a region where dust flux is poorly constrained, the prudent design is to approach at a distance that keeps the risk low, where rare but catastrophic events become very unlikely. That distance may be far enough that even a perfect camera cannot resolve the nucleus. A decision to accept that distance is not a failure of nerve. It is a way to ensure that the craft lives to send home what it was built to send after the adventure ends. It is tempting to say that a small dedicated interceptor would solve these conflicts. In truth, a tiny craft launched on short notice to chase a fast interstellar target faces its own hard math. The time to build, test, and launch is long compared to the weeks a visitor spends within an affordable delta VUS. The technologies that let a small craft navigate autonomously at high speed past a faint target are still maturing. Solar sails, high-thrust cold gas stages, and piggyback deployable scouts are ideas worth nurturing for the next decade, when interstellar visitors may be more common in our logs and launchers more agile. For this encounter, the reality is that the only craft in position are those already busy. If we pursue a flyby, we will be negotiating with schedules set years ago and with resources carefully husbanded for other goals. Suppose a mission has the margins, the geometry is not hostile, and the team is willing. What should the science goals be to justify the risk and the cost? The strongest justification is one that asks a question no other asset can answer in time, and that leads to a clear win or loss for a live hypothesis. If the debate hinges on whether the coma remains carbon dioxide rich near the sun, a spectrometer that can see that band and a plan to catch a spectrum when ground-based observers are blinded by glare are attractive. If the debate hinges on whether the nucleus is unusually compact and dense, a radio Doppler experiment that reads a gravity tug during a close pass earns priority. If the debate hinges on whether optical pulses are narrowband beacons or scattering effects, A high-speed photometer with narrow filters can discriminate. The key is to move beyond the promise of a close picture on a poster and toward the promise of a measurement that will change minds or close doors. The schedule for such a plan is unforgiving. Mid-course corrections must be scheduled early enough that small burns can do the work. Command sequences must be built, tested, and uploaded with margins for retries if a bit error or a ground station outage intervenes. Flight software that was never asked to run at a non-stellar tracking rate may need edits that must pass through safety reviews. A clean room of checklists and interlocks lies between a good idea and a burn. Teams that have done this dance before know that surprises will occur in the last week, and they bake buffers to absorb them. Ethics begins where appetite meets stewardship. A mission is a promise made to a community and to the public that paid to build, launch, and operate a machine over the years. It's data feed careers and test theories that took decades to mature. Repurposing time and propellant is not simply a technical choice, it is a public one. The right question to ask is not how thrilling an intercept would be, it is whether the expected scientific value outweighs the value of the original plan by a margin large enough to justify the diversion, and whether that value is robust to the many ways a high-speed flyby can disappoint. In my experience, when teams put their numbers on the table and speak plainly about probabilities, the romance takes its rightful place beside the accounting. Sometimes the case is strong. Sometimes the case is not. Both answers are honourable when they are earned. There is a modest path that often survives these reviews. It is a light-touch campaign layered atop a mission's existing work, designed to spend as little delta V as possible and to piggyback instrument time during acceptable gaps. Instead of an intercept, you ask for a small set of pointed observations at a safe distance, chosen to maximize the chance that even a non-detection tightens limits. You request a handful of radio tracking sessions bracketing the closest approach to look for any measurable tug in the frequency residuals. You coordinate with ground observers so that combined constraints tell a larger story than any one dataset alone. You keep the craft's primary timeline largely intact. You carry the visitor as a guest rather than as a new master. This path rarely yields the postcard that makes the evening news. It often yields the measurements that survive the next 10 years. It is also worth noting that an exquisite compromise sometimes exists in the form of ride-along software. Missions with flexible command structures can add a diagnostic mode that records raw data for brief windows around predicted times without intruding on the main timeline. A fine-pointing sensor logs at a faster rate. A narrow filter is rotated into place for a few seconds every few minutes. A camera records a short burst at high gain while the main instrument pauses. These tweaks cost almost nothing, carry negligible risk, and can be planned by small teams in weeks. They accept that serendipity favors the prepared and that sometimes the smallest additions to a plan return the largest surprises. My own view is that an intercept, if it comes, should be argued and accepted because it will perform a discriminating test. The language of adventure is intoxicating. The language of hypothesis testing is what we owe the sky. If a flyby can weigh the nucleus well enough to narrow density, if it can read a spectrum in a band Earth cannot see at the right moment, if it can show or rule out structure in the coma at a scale inaccessible from anywhere else, then it repays the cost. If it cannot, then it competes on aesthetic terms with missions fighting for years of careful work. That competition is not fair to anyone. There is a final practical chapter. Whatever we decide, the window is short. A visitor on a hyperbolic path does not loiter. Every week, we delay turns large course changes into small ones with greater fuel cost. Every week we wait is a week lost to testing and rehearsal. The paradox is that waiting for certainty usually means losing the chance to act. This is the moment when an agreed playbook helps. Before a candidate arrives, missions can write down what thresholds of confidence and scientific potential would trigger a repointing review, what margins they will protect no matter what. And what kinds of measurements would count as decisive? When the sky delivers a case, the playbook keeps the argument grounded and the clock honest. We will carry this mindset into the next part, where the measurements we have and the measurements we might win must be weighed against the competing narratives in front of us. A balanced ledger has a place for ordinary physics that looks odd only because our sample is small. It has a place for the extraordinary, which requires a pattern of evidence that resists the easy, natural ways of being wrong. If a repurposed spacecraft joins the effort, its data will matter only insofar as it helps choose between those two paths. That is the standard worth keeping, and it is the bridge to our next question, where we ask what a fair comparison between natural and technological hypotheses should look like, and where we set the threshold at which talk of intention steps out of poetry and into proof. A mystery ripens when different kinds of evidence start to point in different directions. Our traveller has done that. The orbit is cleanly interstellar. The geometry is unusually cooperative in places and uncooperative in others. The chemistry leans hard toward carbon dioxide early, and the light sometimes hints at rhythm. These are ingredients for a debate that could spiral into a posture if we let it. The alternative is to build a fair scale, place each clue carefully, and invite both the natural and the technological hypotheses to make predictions that can be tested without romance. If we do this patiently, the weight of the ordinary or the weight of the extraordinary will reveal itself not because we desire it, but because the ledger does not lie. The first piece of the scale is prior knowledge. In science, a priori is not prejudiced. It is the distilled memory of how often certain explanations have succeeded when the same kinds of clues appeared before. When a comet wakes early and favors a volatile different from water, our prior points to composition, texture, and thermal pathways we do not yet model well. When a light curve flickers, our prior points to rotation, jets, and geometry. When a narrowband radio structure appears once, our prior points to interference and plasma quirks, not to transmitters in the dark. Extraordinary claims require extraordinary evidence, because ordinary claims have already earned our trust by surviving for decades across many cases. A fair comparison begins by admitting that history puts a thumb on the side of nature, and that this thumb can be lifted only by evidence strong enough to move it. The second piece is predictive power. A hypothesis that only explains what we have already seen is a poor one. A good one tells us what to expect tomorrow and risks being wrong. The natural hypothesis does this well when we give it room. If early activity is driven by carbon dioxide near the surface, then as isolation climbs, we should see waterlines strengthen relative to carbon dioxide at distances where crystalline transitions and deeper layers begin to contribute. If jets dominate, the light curve should align with rotation periods derived independently from corkscrew tail features or from periodicities in gas species. If plasma waves are responsible for radio hints, their strength should track the solar wind measured elsewhere and should repeat when the object returns to similar wind conditions, not when a particular facility happens to watch. These predictions are banal only on the surface. They are brave because they can fail in ways that tighten the natural story or make room for something else. The technological hypothesis struggles here unless we sharpen it. To say an artifact could do anything is to say nothing. To be taken seriously, the technological idea must choose mechanisms that a human reader can recognize as engineering. If light pulses are messages, are they narrowband carriers? Are they modulated by a code? Do they lock to barycentric time? And do they repeat with geometry in a way that ignores local conditions in the solar wind? If motion is a message, does it encode a sequence of angles and distances that form a simple pattern when plotted in a frame that natural dynamics would not prefer? If material composition is engineered, does it show ratios or microstructures that fall outside known astrophysical environments in specific, repeatable ways? Each of those is a prediction that risks embarrassment. Without such risks, the idea remains poetry. The third piece is independence. Lines of evidence that seem to agree are useful only if they do not share hidden assumptions or systematics. A light curve and a color curve, taken with the same instrument and the same pipeline, are less independent than a light curve and a radar echo, or a radio feature and a tail morphology map. Independence does not mean hostility between teams. It means different instruments, different methods, different noise, and ideally different calendars. When two independent lines point the same way, the doubt that each carries alone shrinks. When they disagree, we learn what to measure next. A fair scale does not average everything. It looks for clusters of agreement that live on separate foundations. We also need a way to keep score. The human mind likes single numbers. Nature resists them. Still, we can translate a set of observations into a structured comparison by asking in turn how well each hypothesis compresses the data. Does the natural hypothesis explain the early chemistry, the light curve behavior, the radio reports, and the near-sun difficulties with a small set of standard assumptions? Does the technological hypothesis explain the same with fewer arbitrary choices and fewer parameters? If one requires special pleading for every category, while the other leans on known physics, the scale moves. None of this requires formal equations to be useful. A clean paragraph stating which pieces of evidence a hypothesis explains with ease, and which it explains only with extra knobs, is already a discipline. There are classic traps here that we should name so that we step around them. One is the Texas sharpshooter fallacy, painting the bullseye around the holes after the shots are fired. If we proclaim that a given series of dates or angles encodes a message only after we have seen them, we must then predict future marks and accept failure if the marks do not land. Another is p-hacking by the selection of data sets. If we hunt through 100 radio bands and report the one that shows a spike without adjusting our surprise for the 99 that do not, we will render even the honest extraordinary indistinguishable from chance. A third is confirmation bias. If we look harder for flicker when rumors say flicker exists and look more casually when they do not, we will train our telescopes to return our own longing. These are not moral failings. They are ordinary human habits. The cure is public pre-commitment where possible and transparency when it is not. Let us apply the scale to the clues we have been discussing one by one. Begin with chemistry. An early carbon dioxide-rich coma can be natural if birth composition, texture, and thermal evolution favor that volatile. It could also be a sign of processing we do not understand in an interstellar environment, or the outcome of a violent past that removed surface water while leaving deeper carbon dioxide accessible. The technological hypothesis would have to claim either deliberate material choice for a function we can guess at, or a surface treatment that mimics it. The prediction that follows is crisp. As the object warms, if it is natural, the water ratio should rise at a rate consistent with models that bring deeper layers into play. If it does not, if the ratio stays stubbornly high across regimes where water should awaken, we will be obliged to rethink the natural models first. Only if those revised models fail and the stability of the ratio resists. Every textured explanation does the scale shift toward engineered composition, and even then, the shift would be gentle rather than decisive. Consider the light curve. A natural object should show periodicities that, when phase-folded across nights, align with 1 or 2 rotation periods, and their harmonics if the object is tumbling. The amplitude should change with phase angle, and with the filter in ways that track scattering physics. Apparent pulses should weaken under differential photometry corrections if they arise from the atmosphere, and seeing rather than from the object. A technological beacon would insist on narrowband flashes that keep barycentric time independent of weather, keep phase even as instruments change, and appear in bands chosen by engineering convenience, rather than by astrophysical chemistry. The decisive test is repetition under geometry. If pulses recur at the same geometry after an interval long enough that every plausible rotation beat has precessed, then we gain a clue that demands attention. If they fade with better calibration, The file drawer should be open to publish the negative result with the same care that would have greeted a positive. Radio is harder because our environment and our habits sing loudly. The natural hypothesis predicts broadband features shaped by dispersion and plasma lines that move with the solar wind. It predicts strength tied to bow shocks, to draping fields, and to reconnection events. The technological hypothesis predicts narrow carriers, combs of evenly spaced lines, or modulations with symbol structures, each repeating when geometry repeats, and each indifferent to weather and to local equipment noise. The test here is multi-instrument verification with raw voltages and polarization solutions. If a narrow tone appears at two far-separated dishes with a drift rate consistent after barycentric correction and a polarization stable across observations, we take a step. If it appears in one place only, or returns at the same topocentric time of day rather than the same geometry, we step back. The step is small or large, according to how much survives the attempts to break it. Now to motion and the shape of the path. The natural hypothesis offers a distribution of interstellar trajectories shaped by stellar velocities near the Sun and by the layout of observatories and their cadences. Under this model, an object that wanders near the ecliptic and nods at Mars before slipping into glare is a sample drawn from a long tail of chance that our systems are more likely to notice than paths that cross the wrong places at the wrong times. The technological hypothesis must do more than point and marvel. It must be said that the path encodes information by intersecting our assets in a sequence that is unlikely even after selection effects are included. The test is a simulation with real survey schedules. If a dozen trajectories drawn blindly would have yielded similar visibility, the feeling of design dissolves. If only one in many thousands can. And if we then see a second visitor repeat the pattern years later, the balance shifts by increments we could agree on before the test was run. Density and thermal behavior are underrated adjudicators. A nucleus that is unusually dense, given its size, would suggest a structure different from a porous comet and would force the natural hypothesis to consider rare end states of formation or collisional histories. A nucleus that is unusually light and yet holds together near perihelion would require an internal architecture strong enough to resist tidal and thermal stresses in ways that push against our models. Radio Doppler residuals during a spacecraft pass or careful modeling of non-gravitational accelerations across months can constrain mass. Thermal imaging can place limits on thermal inertia, the resistance of a material to temperature change. High thermal inertia would imply rock or metal or compacted ice. Low thermal inertia implies powdery regolith. The technological hypothesis might prefer materials that are smooth and heat quickly, or devices that maintain temperature by design. If we find thermal inertia values and densities in the middle of known comet ranges, the scale pays a tax that technologists must overcome. If we find values at the edges or beyond, the tax shrinks and the debate sharpens. Polarization of scattered light is another lever. Dust grains polarize sunlight in patterns that depend on size, composition, and structure. Over decades, observers have mapped the phase dependence of polarization for many comets. If our traveler shows a polarization curve that lies far outside this envelope, across a range of phase angles, not just at one, and if the curve is stable across filters in a way that resists grain size explanations, then the natural hypothesis must work hard. If the curve sits comfortably among known cases, the technological idea has one less rung to climb. Polarimetry is not glamorous. It is powerful because it is obstinately physical and difficult to fake. We should also talk about failure modes in reasoning that afflict both camps equally. One is overfitting, the act of bending a model with too many parameters until it hugs noise and calls it signal. In the natural camp, this appears when we add jet after jet, phase function after phase function, until the light curve bows. In the technological camp, it appears when we fit a code to a handful of pulses and declare a message. The cure is to withhold part of the data and ask the model to predict it. Another failure mode is survivor bias. We remember the stories where a coincidence landed. We forget the hundreds where it did not. A practice that logs and publishes null searches next to positive findings inoculates us against this bias. A third is narrative creep, where words like engineered and designed slide into sentences because they carry charge, not because the measurements demanded them. A writer can indulge this. A watcher of the sky should not. What threshold should trigger a serious reallocation of attention toward the technological hypothesis? Reasonable people can differ, but one principled answer is this. When at least two independent classes of evidence produce patterns that are both unlikely under the best natural models and coherent with a specific technological mechanism, and when these patterns repeat under geometry in ways that allow prediction and verification, then we owe the extraordinary a seat at the table. Two independent classes might be radio and optical timing, or density and polarization, or motion encoding and narrowband optical flashes. The word independent matters. 3 weak copies of the same phenomenon inside one pipeline do not count. One strong pattern that never recurs does not count. Recurrence under prediction does. There is also a role for humility that does not collapse into timidity. The natural hypothesis is not a single story. It is a family of stories about chemistry, structure, and environment. As data arrive, we should prune that family. If a ratio does not evolve with distance as a thermal model predicts, we should stop saying it might and build a new model. If a light curve refuses to phase fold, no matter how patient we are, we should give up on the simple rotation we prefer and entertain more complicated spin states or surface heterogeneity. The discipline here is to keep the natural camp honest, by forcing it to pay for every added freedom with a prediction that can be checked in the next month, rather than in a paper next year. A natural hypothesis that cannot be falsified is no better than its rival. For those drawn to the technological hypothesis, a complementary humility is warranted. If we think a message is possible, we should design decoding attempts that could fail clearly and teach us something. Try to lock to barycentric time before all else. Test for narrowband structure before clever codes. Make predictions about when a pulse should appear next and share them in advance. If a flyby is proposed to test density or thermal behavior, argue for instrument modes that would produce numbers sturdy enough to move the ledger. Be ready to accept a natural answer delivered by those numbers, even if the pictures are beautiful and the story we wrote for ourselves was better. The mark of a brave hypothesis is the specificity of the tests it will accept. A brief educational aside closes the loop. Hypothesis testing in the field looks less like a courtroom and more like a long farm table covered with jars. Each jar is a line of evidence with a label. As we collect, a few jars begin to fill. Others remain light. The natural and technological hypotheses do not argue with each other across the table. They take turns showing how much they can fit in the jars with the least wasted language. The winner, if there is one, is simply the hypothesis that fills more jars with fewer spilled drops. The rules are plain. No jar counts if it relies on a single unrepeatable event. Jars count more when two different hands can fill them, and a jar filled by a prediction kept is worth more than one filled by a story told afterward. My own suggestion for the threshold at which talk of intent should graduate from metaphor to working premise is conservative. If a narrowband electromagnetic pattern repeats on a schedule tied to barycentric geometry, verified by at least two independent facilities, and if at the same time a photometric pattern with narrow spectral content recurs with the same clock while natural scattering explanations fail under multiband tests, and if a density or thermal measurement lands outside any plausible comet range, then the balance tips. Short of that, every new claim should be routed through the natural filters first, updated as needed, and held to the standard that the extraordinary is obliged to meet. When we build our scale this way, the debate becomes less a clash of temperaments and more a shared effort to keep the jars honest. The cadence we have set in the past parts supports this. Chemistry made predictions for later distances. Light curves made predictions for later geometries. Radio hints made predictions for times when the solar wind turns. The Martian window promised a position and perhaps a profile. A probe redirection, if it happens, will be justified only if it tilts one jar decisively. In the next part, we will step back from the individual jars and look at the factory that fills them. We will talk about how data become claims, how peer review and collaboration shape what the public hears, why negative results are precious, and how open methods and shared timelines protect a community from its own excitement. The scale will still be there when we return, but the hands that weigh with it will be steadier. Behind every headline is a long hallway where photons become numbers, numbers become plots, and plots become claims that other people can test. A telescope takes raw frames that are ugly on purpose. They preserve everything, including bias, hot pixels, and cosmic ray streaks. Calibrations clean the frames, pipelines align fields, and software extracts signals with error bars that matter as much as the signals. Teams log every choice, from background models to aperture sizes, because those choices are where invisible biases hide. I have learned to trust results that show their scaffolding first and their conclusions second. The order disciplines the story. Peer review is not a stamp. It is a speed bump that forces clarity. A good referee asks for alternative fits, for withheld subsets to test overfitting, and for independent reductions by someone who did not write the pipeline. When a result survives that gauntlet, it does not become true. It becomes sturdy enough to use while we keep testing. Preprints accelerate the conversation, but the work is not finished until code, calibration files, and reduction notes are archived where others can rerun them. Reproducibility sounds bureaucratic until you need it. Then it is oxygen. When the evidence around an interstellar visitor is thin and the observing windows are short, reproducibility keeps one team's excitement from becoming everyone's error. Coordination raises the ceiling. A single facility can miss a transient or misread a pattern. A network can watch continuously, split the work across bands, and cross-check in real time. The most useful collaborations decide up front who will chase light curves, who will monitor radio bands, who will attempt narrowband gas imaging, and who will serve as the skeptical auditor with a mandate to break the emerging story. That last role matters. A friendly adversary inside the circle saves weeks of public whiplash later. Tight calendars around perihelion and planetary flybys demand more than goodwill. They demand shared timelines, common file formats, and agreed thresholds for when a candidate feature earns the right to be announced. Negative results are not the absence of news. They are the grid lines on the map. A non-detection at a depth that would have revealed a typical coma sets limits on dust production. A failed search for narrowband radio tones across specified bands at specified times lowers the odds for certain engineered signals. Publishing nulls keeps our priors honest and prevents the file drawer effect from turning chance noise into apparent patterns. My view is simple. If a measurement was precise enough to change a model, had it been positive, it deserves a page when it is negative. Public communication bears responsibility on both sides. Scientists should avoid theatrical certainty while windows are narrow and pipelines are still settling. Audiences should expect plain talk about gaps, safing events, compression artifacts, and scheduling constraints rather than tidy narratives. The best outreach says what we do not know, how we plan to learn it, and what would make us change our minds. That tone protects curiosity from becoming a contest of slogans. When claims about signals or engineered behavior appear, the sober reply is not ridicule, it is a checklist. Did anyone record raw voltages? Did two facilities see the same drift after barycentric correction? Did the light curve survive differential photometry and multiband checks? If the answer is not yet, the conversation can pause without closing. Open methods are an accelerant when used well. Releasing calibrated images, light curves with timestamps, and code that reproduces figures lets other groups audit assumptions within days rather than months. Open data also amplifies mistakes if context is missing. A quick look product should be labeled as such, and a cleaned product should explain what was removed and why. In this story, where early reports of radio hints and optical flicker sit near the edge of significance, the difference between an artifact and a clue may be a few lines of code. Sharing those lines is not optional if we expect trust. The life cycle from proposal to paper to archive is faster now than it was a decade ago, and that is good, but we should resist making speed the measure of value. Some claims deserve to wait for a second night, a second instrument, or a second team. Some deserve a rapid circular because a time-critical decision hangs in the balance. Judging which is part of the craft. My bias is to publish quickly what cannot be repeated and to publish carefully what can, with enough detail that the repetition acts as a true test rather than a performance. Agencies and observatories have a role beyond hardware. They can set norms by asking funded teams to release reduced data and code under clear licenses, by providing repositories that lower the barrier to sharing, and by rewarding meticulous null results in their review criteria. They can also help the public read the room by posting operations logs and latency timelines, so gaps are expected rather than mysterious. Transparency is a cheaper antidote to speculation than any press release after the fact. One more point anchors the rest. The people doing this work are not characters in a plot. They are engineers, students, analysts, and observers making choices under real constraints. When a window is missed or a feed goes dark, it is usually because someone protected a fragile instrument or followed a safety rule that keeps a mission alive. Respecting that context does not weaken skepticism. It aims where it belongs, at the claim, not at the person. If we hold to these practices, the next months will produce a ledger strong enough to weigh big ideas without drama. Chemistry ratios will be reported with uncertainties and cross-instrument checks. Light curves will be tied to geometry and filters. Radio searches will publish both candidates and nulls with raw data for reanalysis. A Mars-side attempt will be documented well enough that even a non-detection will tighten models. And if a repurposed probe contributes, its numbers will be framed as tests, not trophies. That is how evidence grows teeth. From here, the lens widens. Once the measurements settle into the archive and the noise of first contact fades, we are left with a quieter question about what such visitors mean for our culture, our sense of place, and the stories we tell about intelligence and chance. In the next part, we will step outside the lab and ask how interstellar guests reshape imagination without licensing fantasy, and how a responsible narrative can hold wonder and restraint in the same breath. Interstellar guests do more than test our instruments. They test our stories. A visitor on a one-way arc forces us to hold two thoughts at once. First, that we are small in a busy galaxy where rocks, ices, and dust trade star systems as a matter of course. Second, that we can notice, measure, and argue with enough care to turn a fleeting speck into shared knowledge. That pairing is healthy. It keeps imagination awake without letting it run ahead of evidence. Science culture grows when rare events invite many hands. A detection pipeline flags a fast mover. Follow-up teams watch the light, spread the spectrum, and listen on the radio. Modelers sketch thermal waves and tail dynamics. A mission planner checks whether a spacecraft can spare a glance. None of these roles alone owns the truth. Together, they lower the odds that one lab's excitement becomes everyone's mistake. I have come to think of this as a discipline of distributed skepticism. It is not louder than hype. It is sturdier. Imagination still has work to do, and not as decoration. Speculation suggests tests. The idea that motion might carry a message leads directly to simulations of survey visibility and to predictions about recurrence under geometry. The rumor of optical rhythm produces interleaved filter plans and jittered cadences that kill aliases. The whisper of a radio tone pushes observers to record raw voltages, solve for polarization, and schedule on-off pointings with independent dishes. Even the bold thought that engineered materials could ride a comet masquerade becomes useful when it is forced to say what measurements would expose it. Imagination earns its seat by proposing experiments it could lose. History reminds us that new tools routinely rewrite our sense of normal. The first photographic plates that caught faint nebulae stretched the universe beyond the Milky Way. Radio receivers revealed a sky alive with jets, bursts, and background left over from a hotter past. Infrared telescopes found disks around young stars, where planets form. None of those surprises required magic. They required better eyes. An interstellar traveler who wakes early and breathes more carbon dioxide than we expect sits comfortably in that tradition. It may simply be the universe telling us our catalogue was provincial. If so, the lesson is not smaller. It is broader. There is also a civic dimension. Public curiosity is an ally when we respect it. Plain talk about error bars, safing events, and pipeline choices goes further than polished certainty ever will. If an observing feed goes dark near perihelion because instruments protect themselves from glare, say so. If a rumored signal fails a barycentric drift test, explain the test and show the plot. When a non-detection tightens limits on dust production, report it with the same care as a positive result. That posture does not dampen wonder. It keeps it honest. Education thrives on moments like this because concrete puzzles make abstract ideas stick. Orbital geometry turns from vocabulary into a map you can draw. Escape speed becomes more than a number when a hyperbola refuses to close. Spectroscopy stops being a rainbow and becomes a ledger of molecules. Solar wind, once a phrase, becomes the invisible river that sculpts ion tails. A good script leans into those lessons gently, defining terms once, using them cleanly, and returning to them when results change. The reward is a viewer who can follow the debate without picking a team. Responsible storytelling matters because our metaphors steer attention. If we describe a path near the ecliptic as optimized rather than fortunate, we invite a hunt for intent where selection effects already suffice. If we frame a live feed gap as a blackout, we encourage plot over logistics. Words that admit uncertainty permit audiences to wait with us. Extraordinary claims require extraordinary evidence is not a slogan to silence curiosity. It is an ethic to protect it from collapsing under the weight of unearned certainty. There is room here for humility without surrender. We can say that technological hypotheses are on the table in principle and still demand repeatable, multi-instrument patterns tied to geometry before we elevate them. We can say that natural explanations lead by default and still prune them when their predictions fail. We can enjoy the poetry of a traveler threading the ecliptic and still insist on simulations that tell us how often such threading would be noticed. The equilibrium is simple to write and hard to live with. Let strong feelings trigger better measurements, not firmer convictions. Culture also learns from how we handle disappointment. If Mars-side images return only a point and a position, the story is not poorer, it is sharper. If radio campaigns publish nulls with raw data for reanalysis, the next group can try smarter rather than louder. If optical flicker fades under differential photometry and multi-band checks, we gain confidence in our methods. Each tidy negative is a brick. Enough bricks make a wall that can bear the weight of a true surprise later. Finally, a visitor like this reminds us that attention is a resource, pointed at tests that change the ledger, not just at images that flatter our appetite. Support the quiet work of calibration, archiving, and cross-checking. Ask for operations logs and latency timelines so that speculation has less room to bloom in shadows. Celebrate teams that publish code and data alongside claims. Those habits outlive any single comet. They make the next mystery easier to weigh. From here, the narrative bends back to practice. Culture and imagination set the tone, but the next weeks will still turn on measurements. We can name what matters most and why, set expectations that are firm but fair, and show viewers how to follow public data without drowning in noise. In the next part, we will list the specific signs to watch for in light, spectra, radio, and geometry, explain what each would mean for natural or technological stories, and assign honest probabilities that can move as evidence accumulates. Then, with the pieces in place, we will close with a quiet reminder of why patience is not passivity, but the companion of discovery. The next few months are a moving exam. Each window will be brief, but each offers a clean test if we set expectations before the data arrives. The simplest thread to follow is brightness as a function of time and geometry. A natural object that woke early on carbon dioxide should brighten smoothly as isolation rises, with small steps tied to rotation and vent placement, and with color that shifts in ways dust physics predicts. If the light instead arrives in narrow clock-like pulses that keep barycentric time across instruments and filters, then we have a pattern that ordinary jets struggle to mimic. The educational piece behind this is phase angle. Forward scattering can make a coma look more contrasty at small angles, so a rise in pulse strength near small elongations is not enough on its own. The meaningful sign is repetition, when the same geometry returns weeks later while other nights remain uneventful. Spectra are the second thread. If composition drives the story, the ratio of carbon dioxide to water should evolve as deeper layers warm. Expect water features or their proxies to grow relative to carbon dioxide, near and after perihelion, if texture and depth, not design, rule the surface. If the ratio refuses to budge across regimes where water should speak loudly, the natural models must be revised first. Only after those revisions fail should anyone invoke exotic processing or intention. The lesson to keep in view is that spectroscopy measures molecules by their lines and bands. A ratio is never a verdict until multiple instruments, including those beyond Earth's atmosphere, agree. A third sign hides in the shape of the coma. Radial profiles that fall more slowly than nearby stars reveal dust even when the nucleus is unresolved. If those profiles change with time, in ways that match rotation and solar heating, they argue for vents and texture. If they show asymmetries that pivot with geometry, but not with spin, we should ask whether seeing and reduction choices paint that effect. The educational point is AF-Rho, a compact way observers track dust production. A steady rise in AF-Rho near the Sun is routine. Wild swings that do not line up with phase angle or wind, changes demand extra scrutiny before they earn a headline. Tail morphology is a quiet adjudicator. Synchrones and syndines, the curves that map when and what size grains were released, can be fit when images are deep enough. A coherent fit that points to release episodes days or weeks earlier supports a jet-driven history. Kinks or rotations that correlate with solar wind shifts tell you the ion tail is speaking about the field. If a tail points persistently in a direction that defies both gravity plus radiation and the measured magnetic geometry, something in the reduction or the model has slipped. The useful practice here is to compare two vantage points when possible. A view from Mars and a view from Earth on adjacent days can break degeneracies that a single projection cannot. Radio behavior will either fade into plasma weather or harden into something more. Natural expectations are broadband features with dispersion consistent with the column of plasma along the line of sight, strengths that rise near sector boundaries, and variability that tracks measured solar wind conditions. The extraordinary alternative demands narrow tones or sparse combs with repeatable drifts after barycentric correction and with polarization that remains stable across sessions and facilities. Anything that repeats at the same local clock time or only at one observatory belongs in the bin labeled interference. The educational idea beneath this is Doppler drift. A true celestial transmitter will slide in frequency with a slope set by relative motion. A local bird will not respect that slope in the solar system frame. Thermal behavior offers one of the best discriminants and is often the least glamorous. A natural nucleus should show low to moderate thermal inertia, meaning its surface temperature lags behind sunlight and cools quickly. a sign of a dusty crust. High thermal inertia that persists and a smooth phase curve inconsistent with rough, porous materials would press the natural hypothesis hard. If a repurposed spacecraft can record radiometry at close range, or if a space telescope can sample the right infrared bands, even one clean set of numbers could move the ledger more than any pretty picture. The educational piece is that thermal inertia is simply resistance to temperature change. It tells you whether you are dealing with fluff, crust, or compact material. Non-gravitational accelerations deserve a narrow window of attention. As gas vents push on the nucleus, the orbit departs slightly from what pure gravity would predict. Those departures can be fit with simple terms, aligned roughly with the Sun-comet line, or with the velocity vector. If the fit stays small and consistent with measured outgassing, the case for ordinary physics strengthens. If fits grow erratic or require directions that make no physical sense for vents, check the astrometry first before reaching for larger claims. The educational core here is that small forces integrated over months add up. They can teach density indirectly when other methods are out of reach. Fragment searches may matter near and after perihelion. Natural breakups produce small companions that drift along the path, brighten, and fade. Their behavior is chaotic, but explainable with stress and heat. If companions appear and keep formation at separations that defy gravity and outgassing, that is a sign worth chasing carefully with deeper sequences and tighter ephemerides. The lesson is that fragmentation is common. The extraordinary in this channel would be geometry that refuses the rules. What should viewers watch in public data without drowning? Light curves tied to absolute timestamps and filters, not just relative magnitudes, let you phase fold and compare. Narrowband images keyed to classic gas species let you track chemistry with less confusion from dust. Polarimetry plots across phase angle reveal whether scattering sits inside known comet envelopes. Operations logs and latency timelines from solar observatories help you separate planned gaps from anomalies. A cautious observer can follow these threads without choosing a team by asking simple, fair questions. Does a claimed period repeat when geometry repeats? Do spectra from different instruments tell the same ratio story? Do radio drifts match after the same barycentric correction? If the answers trend toward yes, natural explanations earn confidence. If a few trend toward no in a way that resists boring fixes, attention is justified, and so is a higher bar. Expectations deserve numbers, even if they are soft. Given our current knowledge, a natural outcome remains the leading scenario. I would place a high probability on ordinary composition expressed in an unfamiliar balance, early activity governed by carbon dioxide pathways, light curves set by rotation and phase angle, radio structure from plasma environments, and tail behavior that obeys the solar wind. I leave a smaller but non-zero probability for surprises that challenge parts of that story, like an unusually high thermal inertia, a density at an edge of known values, or a rotation state that evolves rapidly under jet torques. The probability that motion itself carries a message, or that engineered signals will pass the strongest tests is not zero in principle, but it remains low until repeating, multi-instrument, geometry-locked patterns appear. Extraordinary claims require extraordinary evidence, because that is how the extraordinary survives the month after the first announcement. A final practical note. Perihelion will likely be a time of rumor and of gaps. The right preparation is to write the checklist now. What would count as a real optical pulse? What radio pattern would force a second look? What spectral ratio shift would require revisiting models? What thermal number would move density out of the comfort zone? If teams agree on those thresholds in public, the debate that follows will be calmer, and the surprises, if they come, will be easier to trust. We have walked the list, not to inflate the mystery, but to place rails alongside it. With rails in place, the closing step can be quiet and honest. In the final part, we will gather the themes into a single breath, return to the simple ethic that curiosity without discipline burns itself out, and leave you with a steady invitation to keep watch, to ask for the plots that matter, and to let the sky change your mind when it has earned the right. We end where we began, with a small light moving on a path that will not close. In July 2025, it slipped into view on a hyperbolic course, retrograde, yet grazing the familiar plane where our planets keep time. It woke early, exhaling more carbon dioxide than water, far from warmth, and it drew us into debates about signals and flicker that demand checks as steady as our curiosity. The calendar's last gifts are near spent, a brief look from the neighbourhood of Mars in early October, and a difficult perihelion near the end of October, when glare and geometry will test our patience more than our instruments. Beyond those dates, the visitor will fade, and only the ledger we kept will remain. What matters now is not which story sounds better, but which measurements survive repetition. Extraordinary claims require extraordinary evidence because wonder is not fragile, it is strengthened by restraint. If radio patterns repeat under barycentric time, if optical rhythms survive across filters and facilities, if composition and thermal behavior refuse the comfort of our models, the ledger will tilt, and we will say so. If the ordinary explains the strange, we will say that too, and learn from the surprise of finding normal in an unfamiliar balance. Thank you for walking this careful path with me. If this pace of measured curiosity feels like your language, leave a comment with the one plot you most want to see next. Subscribe to join the watch, and stay with us as we follow the final windows and report what the sky actually says. The visitor will pass. The habit of listening well can stay. Now, let's give the more daring idea a fair day in court. Is there a way to encode a message in motion without radio, without visible engineering, using only the path itself? In principle, a trajectory could be chosen to maximize the odds of being noticed by a civilization like ours. Such a path would likely cross the ecliptic where survey coverage is densest, pass within a zone where large planets host orbiters that can look outward, and create repeatable geometries that reawaken attention after a forced gap. It might even align encounters so that observational leverage improves over time as a culture's tools mature. There is poetry in that. There is also a burden. For the idea to contribute knowledge rather than romance, it needs predictions that a natural distribution cannot mimic. One prediction would be a sequence of angles and distances that encode a simple pattern across multiple visitors, not just one. If 3 independent interstellar objects in a few decades each traced paths that intersected the same shallow band in the same seasonally favorable windows, with perihelia timed so that ground facilities were forced to hand off to instruments at other worlds, the coincidence argument would strain. Another would be a repeatable relationship between trajectory and the presence of known assets, as if the messenger knew our inventory. A third would be a choreography of motion and light, with optical rhythms that strengthen precisely when visibility to a particular class of telescope is best, then vanish when that class sleeps, in a way that tracks facility schedules rather than physics. Those are hard bars. They should be. If you are going to infer intent from motion, the signature must land outside the wide shadow that chance and selection cast. Between the poles of pure chance and pure design sits a region where language can mislead. We often call a path efficient because it offers multiple observation modes, but nature produces efficiency without meaning. The ecliptic is busy because it is where the momentum went when the solar nebula flattened. The nodes where a retrograde visitor crosses that plane are baked into its orbital elements not tuned for our benefit. Near planetary orbits, the combination of forward scattering and shorter geocentric distance can raise brightness in predictable ways. It will feel like a performance because our attention wakes in the same windows. The word optimized does a lot of work here for our imaginations. A better word is fortunate. I will put my own view plainly. Motion that seems considerate of our instruments is not persuasive evidence on its own, not because intent is impossible, but because the universe and our attention conspire to create that feeling regularly. There is a discipline that keeps us honest. Start with the null model that the object is a random draw from a physically reasonable distribution of interstellar paths. Pass that draw through a faithful model of our surveys. Compute how often you would see what you saw. If the answer falls in a comfortable range, nod and move on. If the answer is stubbornly small across many assumptions, then you have earned the right to raise the question of design one step higher. In either case, and this matters, document the assumptions so that others can run the same experiment with different dials. Shared simulators turn hunches into arguments. There is another kind of test that avoids simulation entirely. It uses time. If motion carries a message, the message should survive when the instruments change. Imagine that an object presents a favorable geometry to a particular orbiter in 1 month and to an unrelated ground network several months later. If the same phase angle dependent optical rhythm strengthens in both frames, that is physics. If instead the rhythm aligns with the orbiter's duty cycle and vanishes when only ground telescopes watch in equally good geometry, that is suspicious. Likewise, in radio, if a narrow feature recurs when 2 far-apart facilities point at the same place, that is compelling. If it recurs only when one of them watches, that is less so. Motion and instrument schedules are both clocks. A message tied to motion should not care which clock we use. All of this speaks to a virtue that rarely makes headlines. Restraint is not indifference. It is the room in which real surprises can stand up. If we declare design every time a trajectory hands us a convenient window, we will teach ourselves to see intention in the curve of a river and the tilt of a hill. If we never ask, we will miss the one time a pattern refuses to die under careful blows. The balance is simple to say and hard to live. Let the default be chance filtered by selection. Let the exception grow slowly under repeated tests, crossing thresholds agreed in advance. Above all, remember that extraordinary claims require extraordinary evidence, because ordinary claims already weight of history behind them. A brief educational detour grounds the rest. The ecliptic is the plane defined by Earth's orbit. Inclination measures how much an orbit tilts from that plane. Retrograde means the motion is opposite to the planet's spin around the sun. The line of nodes marks where a tilted orbit crosses the plane. The argument of perihelion and the longitude of the ascending node set how the ellipse or hyperbola sits in space. None of these numbers knows who we are. They are the grammar of motion in a central potential. When we infer meaning from them, we are often reading our own reflection. Yet there is a healthy way to channel the itch for meaning. Treat visibility as a resource to be optimized by us. If a path presents even a lukewarm window, prepare instruments and schedules so that the window becomes a lever. Stack short exposures to beat trailing losses. Spread filters to read color during suspected pulses. Coordinate at 2 longitudes so that aliasing is avoided. If the object is going to pass within reach of an orbiter's camera, plan what integration times, tracking rates, and compression settings will preserve the shape of a point-like nucleus against the blur of a dust coma. In that sense, we can make optimization real. We can turn a merely decent encounter into one that settles a debate not by finding intention in motion, but by applying intention to observation. When you watch the path with this mindset, the next chapter stops looking like choreography and starts looking like logistics. The impending pass by the orbital domain of Mars is not a wink. It is a tractable opportunity defined by angles and by the capabilities of a camera that was built to read dunes and dust devils and now, for a night, can try to catch a traveler against a star field. The challenge is technical rather than metaphysical. Relative speeds will be high. The apparent motion will be brisk. The target will be faint and embedded in a haze of its own making. Exposure times will sit on the knife edge between enough signal and too much smear. Tracking rates will have to be computed with care and rehearsed. Telemetry will have to be budgeted so that raw frames arrive on the ground without pushing aside the orbiter's primary science for long. There is a personal comfort in that pivot from speculation to plan. When motion feels like intent, I remind myself that geometry gives gifts and takes them away without malice. When we receive a gift, we do not owe the sky a story. We owe it competence. In the next part, we will fold the map, pull the camera outward to Mars, and ask what a carefully executed attempt at high-resolution imaging can really deliver. We will talk about tracking a faint point crawling across an unfamiliar background, about exposure ladders and stacking, about what a single sharp pixel could mean for our estimates of size, and for the models that try to explain why this visitor woke early and breathed in a different balance than we expected. The calendar gives us one favor before the glare takes the stage. In early October, the visitor passes near the orbital domain of Mars. Near is an astronomer's word that still means far in human terms. But for cameras riding around the red planet, that proximity can translate into a measurable advantage. The Sun Object Observer Triangle looks friendlier from Mars than from Earth on those dates. Distances shrink slightly. Phase angles fall into a range where dust scattering can lift brightness. Most importantly, an orbiter above Mars can point outward into a darker sky than a twilight-bound telescope on Earth can manage when elongation is small. If there is a moment to catch a sharper glimpse before perihelion hides the view, this is it. The opportunity is not romantic. It is technical. That is why it matters. Imagining a fast, faint target from orbit is a different craft than mapping dunes or layered rock. The principles, though, are the same ones we have practiced from the ground. Apparent size sets whether the nucleus is anything more than a point spread, ballooned by optics and motion. Apparent motion sets the maximum exposure time before smearing devours contrast. Surface bright scenes want short exposures and low gains. Starfield scenes want longer exposures, careful pointing, and a noise budget that favors read stability. The object here complicates each of those knobs. Its motion across the Martian sky will be brisk compared to the slow drift of a crater floor. Its brightness will be low and embedded in a weak coma that spreads photons thinly. The recipe will need rehearsal, and rehearsal, in this case, means simulation. Start with geometry. From Mars, the visitor's angular speed is driven by the vector difference between its space velocity and the orbiter's own path around the planet. That relative motion is not a constant over the pass. It can wax and wane over hours. A planning team will calculate a track on the sky to sub-arc-second precision, then translate that track into pointing rates the spacecraft can command. A crucial decision follows. Do you track the stars and let the object trail? Or do you command a non-sidereal rate that keeps the object pinned while the stars streak? For surface images repurposed for skywork, non-sidereal tracking is not always a standard mode. If the hardware and software allow it, keeping the object still on the detector pays dividends. It concentrates flux into fewer pixels, lifts the signal above the background, and makes post-processing easier. If the platform cannot track at that rate, you accept trailing and optimize in other ways. Exposure length is the second lever. Too short and red noise, and overhead chew up the budget. Too long and the target stretches into a thin line that lowers the peak signal and shaves the chance of a detection. A common tactic when time and telemetry allow is an exposure ladder. You take a sequence of frames at a range of durations, from safe short shots that freeze the motion to risky long ones that hope to gather enough photons to see the outer coma even if the core smears. Later, you can register the short frames in the object's moving frame and stack them to recreate a longer effective exposure while controlling the smear in software. The longer frames may reveal broader dust features or faint field stars for an astrometric tie-in. When the window is narrow, you cannot be precise with a single perfect setting. You hedge across settings so that at least one set lands on the right side of the trade. Pointing alone will not save a weak signal if the background is unforgiving. The Martian sky is dark above the limb, but scattered light from the planet itself can haunt an outward-pointing camera if the boresight passes near the bright crescent of Mars. Engineers will map stray light fields to choose roll angles that keep bright edges out of the optical path. They will ask, whether a baffle was designed for skywork or for surface work, and how internal reflections behave when stars, rather than sand, carry the scene. Stray light is the bane of small signals. It adds a slope to the background that a simple flat field cannot undo. If you know it is coming, you can pivot the spacecraft to place the gradient along a direction that later median filtering removes without touching a compact coma.